In this chapter, we will look into internal flows through pipes, elbows, teeth, valves, and many others, as in this oil refinery are found in nearly every industry. So these are the reasons why we are interested in internal. The objectives are to have a deeper understanding of laminar and turbulence flow in pipes and the analysis of fully developed flow. Second, to calculate the major and minor losses associated with pipe flow in piping networks and to determine the pumping power requirements. And third, to understand various velocity and flow rate measurement techniques and learn their advantages and disadvantages. Introduction: liquid or gas flow through pipes or ducts is commonly used in heating and cooling applications and fluid distribution networks. So for fluids, normally we use pipe. For gas flow, we use ducts. Okay, so here are the example of ducts. Is a rectangular duct, and then we have a circular pipe. Okay, and the fluid in such applications is usually forced to flow by a fan or a pump through a flow section. So here for water, we will use a pump, but for air normally we use fan. Okay, we pay particular attention to friction, which is directly related to pressure drop and head loss during flow through pipes and ducts. So for example, we know that P equals to rho GH. So here's the pressure Pascal, and here's the head, okay, in meter. So when the water or air flowing through this piping system, we will have a friction loss. Friction loss is either reported in the forms of pressure drop or reported as a head loss. Alright. So the pressure drop is then used to determine the pumping power requirement. So if we know how much pressure is lost, or if we know how much head is lost, so we can use that to determine how much power is required, so that we can overcome this friction loss. Okay, so what happened to the friction loss? The friction loss will take away the energy. As a result, the air or the water flowing through the piping system, they will flow at a slower speed. So the reason we pump the water or we pump the air is that we want to move the fluid or the liquid, the air or the liquid to a certain place in a given time. So when there is a head loss, the pumping, the flow process will be slower, so it takes more time. So as a result, if you want to achieve the same flow rate or the same mass flow rate or the same volumetric flow rate, we need to determine what is the head loss or the pressure loss, so that we can increase the power of the pump or the fan, so that we can achieve the flow rate or the mass flow rate that we want. Okay, so here this figure shows the circular pipes and the rectangular duct. So the circular pipes can withstand larger pressure difference between inside and the outside without undergoing any significant distortion. So it can withstand high pressure. But for non-circular pipe like this duct system, okay, the duct casing, this one cannot withstand high pressure. So if you look here, water can be pumped in the circular pipe system up to 50 atm, 50 atmospheric pressure, whereas in the air flow system, it can normally only lower pressure. So in this case, it shows to you is 1.2 atmospheric pressure. In a piping system, so we want to find the velocity in the pipe. So one of the common velocity value that we want to find is the average velocity. So if you look at the flow profile developed in the piping system, so near the wall, the velocity is near to 0. Okay, and in the middle of the pipe, you have a maximum velocity. So if you sum up this flow velocity profile and you take an average of it, you get V average. So from here we can find that the average velocity is defined as the average speed through a cross section. For fully developed laminar pipe flow, V average is half of the maximum velocity. So when you find the average velocity for the velocity profile, you get about half of the maximum velocity. So it's not about, it's actually half of the maximum velocity. And this case is true for a fully developed laminar flow, laminar pipe flow. So for laminar flow, you get half. The average velocity is half of the maximum value. Alright. So the theoretical solutions are obtained only for a few simple cases, such as fully developed laminar flow in a circular pipe. So we only have a good idea how theoretically this laminar flow are being developed, and when we try to estimate the average velocity, we know that the average velocity is half of the maximum value. But in most cases, we don't have that kind of information. Therefore, we must rely on experimental result and empirical relation for most fluid flow problem rather than a closed analytical form, closed form analytical solution. So if you anything that deviate from laminar pipe flow, therefore this V average is half the value of maximum velocity is no longer true. So this case is only true for laminar flow in a pipe. Okay, so in here it shows to you how we actually determine the average velocity. First, we know that the mass flow rate is given by rho AV. So rho AV is simply the integration of the velocity profile that change within the pipe radius, and then of course this will change according to the area in the pipe. Okay, the area start from the middle of the pipe. All right. So the value of the average velocity V average at some streamwise cross section is determined from the requirement that the conservation of mass principle be satisfied. That's why we determine it from mass flow rate, because mass flow rate it conserves the mass, and if we determine it from this perspective, our estimation is accurate rather than determined from the volumetric flow rate. Okay, so mass flow rate equals to rho AV. Okay, so in the integration form is rho velocity as a function of radius, and then and multiply with the differentiation of the area of the pipe, and then if you want to find the average velocity, so you just divide by the what I call the total the density and the area and the total area, right? So you just divide by the rho and area, the cross sectional area. Therefore, we get the average velocity. So in this case, we realize that dA can be expanded, okay, to 2 pi r after the derivative. Okay, then we could cancel out the pi value, the density value. So you can see that this density will be taken out from the integration. The reason we do that because the average velocity is for incompressible flow in a circular pipe of radius r. So because this is incompressible flow, the density can be taken out and cancel out. Therefore, we only left with a more simple form of the integration equation, right? So this is how the average velocity is being determined for a circular pipe. So now we look into laminar and turbulent flows. Okay, laminar flow is encountered when highly viscous fluid such as oil flow in small pipes or narrow passages. So what does it mean is that in a high viscous condition of the fluid, the flow is laminar. So when the fluid is less viscous, most likely you will encounter turbulence flow or transition flow, right? So the easiest way to imagine laminar flow is that you have an injected dye into the fluid flow system, and you can see that the fluid that in red color will flow in a straight line. So if you see a flow in a straight line, basically you have a laminar flow. And then if you inject the ink into the fluid system, but you can see a small straight line, and then followed by a zigzag motion of the dye, okay, and therefore this is what we call turbulence flow. All right, so laminar is a smooth, streamlined, and highly ordered motion. Turbulence, the velocity fluctuation and highly disordered motion. So this is highly disordered, and this is highly ordered. Okay, ordered motion. And that is another stage we call it transition. The flow fluctuates between laminar and turbulence flow. So sometimes laminar, sometimes turbulent, sometimes laminar, sometimes turbulence. Okay, so that is a transition. Okay, yeah. So most flow encountered in practice are turbulence flow. All right, especially air flow. Okay, so here is a candlestick that is burning, and you can see that uh, we have a laminar flow initially, and then end up with a turbulence flow in the end. Reynolds number is used to indicate to determine which flow conditions the fluids are in. So for example, laminar, turbulence, or transition. So this will depends on the Reynolds number. So the transition from laminar to turbulence flow depends on the geometry of the piping system, the surface roughness of the system, the flow velocity of the fluid, the surface temperature of the piping system, and the types of fluids that flow in the piping system. So the flow regime depends only on the ratio, the initial force to the viscous force. So if you take initial force 2 divided by viscous force, then you get Reynolds number. So Reynolds number is given by initial force divided by viscous force. So here this figure show the initial force divided by viscous force give the Reynolds number. So the initial force is given by rho, the rho of the fluid flowing in the piping system, the velocity of the fluid, average velocity, and the length of the not the length. This is the what you call the diameter. Okay, the width of or in this case diameter of the pipe. All right. So if it's dark, then will be the height of the pipe, something like that. All right. Then rho v square, rho v average square, and multiply with L square divided by the dynamic viscosity, okay, the resistant dynamic viscosity, multiply with average velocity and the diameter, okay, or the height of the what you call the duct, okay, something like that. And then it can be simplified further. You will get rho vd, okay, rho vd, okay, rho vd over dynamic viscosity. And if you take dynamic viscosity divide with the density of the fluid, therefore you will get this kinematic viscosity. All right, so here's a kinematic viscosity. All right, so rho vd divided by mu, okay, mu is the dynamic viscosity, or you can simplify here to a shorter form, vd divided by kinematic viscosity. All right, so at large Reynolds number, the initial force, okay, at a large Reynolds number, the inertial force, okay, the inertial force which are proportional to the fluid density, okay, fluid density, and square of fluid velocity are large relative to the viscous force. So what I try to say is that at large Reynolds number, the initial value is very large compared to the viscous force. So thus the viscous force cannot prevent random and rapid fluctuation of the fluid. So end up we get turbulence. So when the initial force is very large, therefore this viscous force cannot keep the fluid in laminar flow. End up you get turbulence flow. All right. At small or moderate Reynolds number, the viscous force are large enough to suppress this fluctuation and keep the fluid in line, laminar. So when the viscous force is large, end up you get laminar flow. So example, if you use a chopstick or if you use a stick to stir a pool of water, then the pool of water would move vigorously and maybe near or in turbulence flow. But if you replace the pool of water with honey, for example, or with oil, the oil from your car, the oil from your motorcycle, so if you take a stick or a chopstick to stir a pool of oil, you could see that the oil would move, but move in the laminar form. So it will move very gently, okay. But if you stir a pool of water, then you can see that the flow can be easily done, can flow very, very fast because the initial force is very, very large, and then it can flow very, very vigorously and cause creation of sound. So all these kind of sounds are actually is a result of frictions, energy loss. Okay, so it just tells you that it just tells you that the viscous force is not there to keep the flow in laminar flow. All right. And then critical Reynolds number, okay, RE critical, the Reynolds number at which the flow becomes turbulence, right? So the value of the critical Reynolds number is different for different geometries and flow conditions. All right. In the previous slide, I showed you there's a Reynolds number require the rho density of the liquid, velocity of the liquid average, and then the diameter of the pipe over the dynamic viscosity. So now I showed you how do we determine the D. Okay. So the D not necessarily referring to the diameter. If it's circular pipe, yes, it is referring to the diameter. But for non-circular pipe, we can actually determine it differently. Okay, so the actual formula for D is actually 4 AC over P. So the AC is the cross-sectional area, and the P is the parameter. So for flow through non-circular pipe, the Reynolds number is based on the hydraulic diameter. So the DH is called the hydraulic diameter. All right. So this D is the hydraulic diameter. All right. So for flow in the circular pipe, we have a Reynolds number less than 2,300, which is laminar flow. Between 2,300 and 10,000 is called transitional flow. For Reynolds number greater than 10,000 is called turbulence flow. So in the transitional flow region, between 2,300 and 10,000 Reynolds number, the flow switches between laminar and turbulence seemingly random. So here you can see that you have this turbulence flow, and then followed by laminar flow, and then turbulence flow. So this thing happen because the Reynolds number fall between 2,300 and 10,000. All right. So now, if you want to determine the hydraulic parameter, we want to determine this hydraulic parameter, this hydraulic diameter. Okay, hydraulic diameter. So we can use this formula. DH equals to 4AC, 4A cross-sectional area over perimeter. Is defined such that it reduces to ordinary diameter for circular tube. So if you use it for circular tube, we take 4AC over perimeter. So we see that the area, cross-sectional area for circular pipe, we have a pi r square. So pi r square is also equals to pi d square over 4. And then the parameter is 2 pi r for circular pipe. And then it can be written as pi d because 2r is actually the diameter. 2 radius value is actually the diameter. So if we take the A divided by the P, then we take the A divided by the P, and then here you multiply with 4, you end up with D, okay, the diameter. So as a result, this is the diameter for circular pipe. All right. So when it's non-circular, so D would become this hydraulic diameter. So you have to determine it for different dimension of the piping system. Right. For square duct, if you find the A is actually A minus A multiplied with A, you got AA or A square. Then the parameter is 4 times the A value. Okay, A plus A plus A plus A. So you get a parameter of 4A. Then if you take 4A divided by 4 multiplied by the cross-sectional area, but divided by the parameter, you get 4A square divided by 4A, then you end up with A. So this DH become A. So when you calculate the Reynolds number, so this D will become A value. All right. So we do the same for rectangular duct as well as channel flow. So you end up with different hydraulic diameter. All right, different hydraulic diameter. So this slide shows the entrance region. Okay. So if you see that this is a long pipe, and then there's a fluid flowing from the left side. So as the fluid enter the system, so initially there is not much of resistance from the pipe, but as the fluid flow deeper and deeper into the pipe system, the fluid will feel more of the drag resulted by the pipe wall. So the pipe wall create a drag, okay, on the fluid flowing in the system. So this drag initially is not present, but gradually become more significant, deeper and deeper into the center. So as that happen, we start to develop what you call this velocity profile. Okay, so the velocity profile initially is not significant. It's not they are means that they are all the same, equivalent. As it flow deeper, so the drag from the wall start to move deeper and deeper into the center of the pipe. All right, so basically there are three things we would like to talk about here. We talk about the velocity boundary layer. So the velocity boundary layer is a region of flow in which the effects of viscous shearing forces caused by fluid viscosity are felt. So the viscous shearing forces caused by the fluid viscosity and also the effect of the wall are being felt. It's more significant over time. All right, and then the boundary layer region. So this is the boundary layer region. The viscous effect and velocity changes are significant. So the changes of velocity and the effects of viscosity are very, very significant in this red line. Okay, and then we have the irrotational core flow region. The frictional effects are negligible and the velocity remain essentially constant in the radial direction. So initially it flows as a liquid enter the pipe. All the velocity profile are more or less the same. As it moves deeper and deeper, the center is eventually moving at a greater speed than the flow velocity profile near the wall. So until the end of it, you will have a fully developed velocity profile. Okay, then and at the center they don't feel much of the resistance, but until the effect of the viscosity is felt by felt in the middle, then you start to feel the effect of the drag created by the piping wall. Okay, so the distance that it takes to develop this, we call it the hydrodynamic entrance region. Okay, so this is the distance that it takes for this effect to take place. Once that hydrodynamic entrance region done, then you have a fully developed velocity profile. This shape would the velocity profile of this shape would stay the same throughout the pipe as long as the diameter of the pipe does not change. So this is how the velocity profile are being developed. So this figure shows the development of velocity boundary layer in the pipe. The developed average velocity profile is parabolic in laminar flow, but somewhat flatter and fuller in a turbulence flow. So it means in a turbulence flow, you don't get a more sharp velocity profile, you get a flatter shape. Okay, flatter shape. And here, always remember that the average velocity is never the maximum velocity. Okay, the maximum velocity is at the tip of the velocity profile, and then the average velocity for laminar flow, you get half of the velocity, maximum velocity. All right. So just now I mentioned to you that you need a distance for the velocity profile to be fully developed. So the distance that required is called hydrodynamic entrance region, and then the region after that is called hydrodynamically fully developed region. Okay. Okay, so here we talk about the hydrodynamic entrance region. So the region from the pipe inlet to the point at which the boundary layer merges at the center. Okay, so hydrodynamic entrance region already shown here. Okay, and the hydrodynamically entry length LH, the length of this region. So it is basically the length of this region. We from here to here, you can label it as a LH, length of this hydrodynamic entrance region. And then hydrodynamically developing flow, the flow in the entrance region, this is the region where the velocity profile develops. So velocity profile develops, you can see from here to here, this is where the velocity profile develop. And if you it looks to me that the definition for hydrodynamically developing profile and the hydrodynamic entrance region, they are more or less the same. Perhaps there are some small difference. Okay, so the hydrodynamically fully developed region, the region beyond the entrance region in which the velocity profile is fully developed and remain constant. So hydrodynamically fully developed region. So here is a hydrodynamically fully developed region. Okay, so after this region is a fully developed. All right, and then the fully developed when both the velocity profile, the normalized temperature profile remain unchanged. Okay, so if you can look at this diagram, when it's fully developed, as it moves down, the velocity profile remain unchanged. Okay, stay the same as it moves down. Okay, another way to look at this is that we can take the derivative of the velocity. So if you look here, it's a hydrodynamically fully developed condition where the velocity profile as a function of radius, as a function of x is a flow directions. Okay, so if you take du dx, you get 0 because the velocity does not change with x. Okay, so this is x, so it means the velocity profile will stay the same even though he moved down the piping system. So it means you only have velocity profile that only change with radius. Okay, so no change of velocity in the x direction. So in the fully developed flow region of a pipe, the velocity profile does not change downstream. So the velocity profile remain the same downstream, and thus the wall shear stress remain constant as well. So as I mentioned to you, the resistance created by the wall that created this velocity profile, the resistance will stay the same as the velocity profile as the fluid move down the piping system, and the drag force, the shear stress is become constant. All right. So here we have a figure shows the development of the wall shear stress. So this tau W is the wall shear stress, and you have a graph showing how the variations of wall shear stress through the entrance region as well as the fully developed region. This is basically the water flow from the left side into the right side of the pipe. Okay, so basically the water coming from a larger reservoir, and once it enters the pipe, it will have to go through this what I call velocity profile development. So until after the entrance region, then only you get a fully developed velocity profile, right? So the pressure drop is higher in the entrance region of the pipe. So what do you mean by pressure drop is higher? So it means if you have a greater wall shear stress, then you have a greater friction. That's what it means. So when you have more friction, you have more loss. So more loss leads to more pressure drop. All right. So pressure drop means you lost in the energy, right? Because for the water to flow through, you need to have certain amount of pressure. So once you have pressure drop, means the pressure that required to push the water into the system has been lost. That's what it means. All right. And the effects of entrance region is always to increase the average friction factor for the entire pipe. So you see, once the pipe, when the flow profile becomes fully developed, the wall shear stress becoming a constant. But at the as the water enter the pipe, you can see that shear stress, the wall shear stress is the highest. Okay, the resistance is the highest, and then it gradually drops. So this great amount of shear stress actually increases the average friction factor of the entire pipe. All right. So that's why the entrance region is very important to consider, right? And here you can see the diagram showing the pipe, the flow directions of the water of the fluid, and then you can the length of the line here is against the flow directions. This is showing this resistance. So you get a greater resistance near to the entry point, and then gradually becoming smaller and smaller, and then become constant at the end of the entrance region. So in the fully developed region, the wall shear stress become a constant. So the variations of the wall shear stress in the flow direction for pipe in a pipe from the entrance region into the fully developed region. So from very large to gradually decrease and then become a constant in the fully developed region for the wall shear stress. So the pressure drop in this region is the greatest, and then the pressure drop after the entrance region is a constant. So you have a constant pressure drop, or we call it head loss, after the entrance region. Now let's look into entry length. It's important to estimate the frictional head loss. So the hydrodynamic entry length. So this is the hydrodynamic entry length. So the entry region, the length of the entry region. So it's called the hydrodynamic entry length, or LH. Okay, is usually taken to be the distance from the pipe entrance, okay, from the pipe entrance to where the wall shear stress and thus the friction factors reaches about 2% of the fully developed value. Okay, so if you take the laminar, the entry length and the hydrodynamic entry length LH, divide by the hydraulic diameter. Is it correct? Hydraulic diameter. Let's check. Okay, hydraulic diameter DH. So you take the ratio of that, you get about 0.05 of the Reynolds number. Okay, so that's true for laminar flow. So the hydrodynamic entry length for the laminar flow can be estimated using this equation. If for turbulence flow is 1.359 multiplied with the Reynolds number to the power 1 to 4. Okay, and you can also use approximation for turbulence. You can use a factor of 10. All right. So the pipe used in practice are usually several times the length of the entry for the length of the entrance region. Okay, so this is the entrance region. So if you know you have a certain length of this hydrodynamic entry length, then you design your pipe 3-4 times. Okay, 3-4 times or maybe several times the length of the entrance region, and thus the flow through the pipe is often assumed to be fully developed for the entire length of the pipe. So after this entrance region, after this hydrodynamic entry length, you get a fully developed velocity profile. All right, that's what it means. Now this simplistic approach gives reasonable result for long pipe, but sometimes poor result for short one, since it underpredict the wall shear stress and thus the friction factor. The reason we need the length of the pipe that's several times the hydrodynamic entry length means we want the pipe to be longer than this what we call entrance region, is because we want the velocity profile to be fully developed. So once the velocity profile is fully developed, and then you let the water flow several times longer than this entry level, this hydrodynamic entry length, then you can get a good estimate of this what we call hydrodynamic entry length. Okay, or eventually you can also estimate the friction, okay, friction head loss more accurately. Okay, so now let us look into this laminar flow in pipes. Okay, so we consider steady laminar incompressible flow of a fluid with constant properties in a fully developed region of a straight circular pipe. Okay, so means that steady means there's no change in the velocity is always constant. Laminar means there's no crossover of the streamline. The streamline is always parallel to one another. Incompressible flow basically means there's no change in the density of the fluid. Okay, and in a fully developed laminar flow, each fluid particle move in a constant axial velocity along the streamline. All right, and the velocity profile UR remain unchanged. So if you have a velocity profile something like this, it will remain the same as it moves down. Okay, so the velocity profile near the wall is always with this line, and as it moves deeper into the pipe, it also stay the same in terms of the length and directions. So they never cross another, and they never change in terms of the speed at different radius of the pipe. Okay, so the water at different radius flow at different velocity, and this velocity stay the same all the time. All right, they never change in the magnitude or direction. Okay, remain unchanged in the flow direction, and there is no motions of the radial directions. Means the velocity profile will not cross over to one another, so they just flow in the x direction only. Okay, and thus the velocity component in the direction normal to the pipe axis is everywhere zero. So no flow in the vertical direction. There is only flow in the horizontal direction only. Okay, only the particle the fluid particle only move in the horizontal, and the fluid particle does not move in the vertical. No flow in the vertical. Okay, there is no acceleration since the flow is steady. So the velocity, the V1, if you compare V1 with V2, it's always the same. So v1 is equals to v2. So the velocity is always the same. As a result, there's no acceleration. Okay, since the flow is steady and fully developed. All right. So to this equation, okay, this equation is used to represent the changes of pressure with space with different under the influence of viscosity and shear stress. Okay, shear stress. Okay, the viscosity and also the pressure force. Okay, so if you look into this fluid flow in the system, you are influenced by two force. One is the force that force the fluid to flow through the pipe, and the other force is the resistance. All right. So the force that force the fluid to flow through the pipe is the pressure, and the one that try to stop the fluid from flowing through the pipe is the resistance. So the resistance is a shear stress. Okay, shear stress that is related to the viscosity, the dynamic viscosity. All right. So we can imagine that there's a what I call a segment. Okay, a ring-shaped differential fluid element of radius r with a thickness dr. Okay, so this it's like a what I call this what I call fictional ring-shaped differential fluid element of radius r. Okay, radius r, and then it has a thickness dr. All right, it has a length of dx. Okay, the length of dx oriented coaxially with the horizontal pipe in a fully developed laminar flow. So we know there's two forces in place. One is the pressure, the other one is resistance. Okay, due to viscosity. So we try to draw a simple diagram based on this. We put it here. So we have a force pushing from behind for the fluid to move from left to right, and then of course there will be a counter force pressure. Okay, there will be a counter pressure force, and then at the same time we have a resistance due to viscosity of the fluid at the bottom, and the resistance or the viscosity friction at the top. Okay, so they are acting against each other. All right, so we can write what I call force balance equation for this. So we take this pressure force. So we take the pressure multiply with the area, then we get the pressure force acting from the left to the right. So P multiplied by with dA. Okay, dA, a small area. So the dA is equals to 2 pi r dr. All right, after we differentiate the area, so we get from dA become 2 pi r dr, and then this force from left to right will be counterbalanced by a force from the right to the left. Okay, from the right to the left, there's another counter force, and when the first pressure force act at the direction at the distance of x, then the counter force is acting at the direction of x plus dx. Okay, so same force acting in different directions, so we have a P multiplied with dA as well from a different direction. This dA again is 2 pi r dr. Okay, all right, so if it's the force is acting in the x direction, you have a positive sign, and then the pressure force acting in the opposite direction, you have a negative sign. So you have this minus this value. So we have a balance of pressure force, and then the other one is the resistance force. Okay, resistance. So we have this shear stress acting in different directions. We have one that is towards the x direction. So you have a tau. So you multiply with the area. Okay, you multiply with the area. All right, so the area depends on the area of the cylinder. So the area of the cylinder, you will have to find the parameter of the cylinder, which is 2 pi r. Okay, and then you multiply with the length, with the horizontal length of the what I call ring shape. Okay, of the ring shape, which is dx. So you have 2 pi r, the parameter of the cylinder, multiply with the length of the cylinder. So you get 2 pi r dx, and then you multiply with the shear stress, and then you'll get the force, okay, acting in this x direction. So it's it's a tau r, okay, tau r, and then another shear stress acting in the opposite direction. Then of course it's the same thing, it's a same shear stress but at the different directions, and this time it is not acting at the bottom but acting at the top. So this shear stress force, this force of shear stress acting at the bottom, and then you have another shear stress force acting at the top. All right, so they are against each other. All right, so here the tau r is positive because it's in the directions of the x, and then this the tau r plus dr is in the opposite direction of the x, so you have a negative sign here. And then these two force, pressure force and the force resulted by the shear stress due to viscosity of the fluid and also the wall of the cylinder, and you get this equals to 0. So we can divide this whole thing. First we can cancel out 2 pi, okay, we can cancel out 2 pi, and then the 2 pi for all these 4 terms can be cancelled out, and then we divide it with dx and dr, so you get these forms of equation, okay, and then you realize that px plus dx minus px is actually equals to dp, okay, so dp divided by dx, same thing, this r tau r dr minus r tau r is actually this differential of r tau, okay, so you just differential of r tau divided by dr. All right, and then if you try to simplify this equation further, you can actually include this tau. You know, tau is a result of is a shear stress, is a result of viscosity, and also the result of dynamic viscosity and the velocity velocity gradient, okay, velocity gradient du over dr. The u is the velocity, all right, and r is the radius. So this du dr is a velocity gradient. So if you replace this into for tau, and then you try to rearrange this equation, you will get this form. All right, okay. Okay, continue from the previous slides, okay, these slides, right? So we already developed these slides to show the pressure gradient in relation to the velocity profile in the radius of the pipe, and then we can also derive another equation for all the fluid in the pipe. So what can we do? We draw this simplistic diagram. It shows that there's a pressure force coming from the left and pressure force coming from the right, and then we have this the wall, the shear stress from the wall. All right, so we write this force balance equation. So P multiplied with pi r, P divided by P multiplied with the area which is pi r r squared. So the r is the radius, okay, of the pipe. All right, and then the other one coming in the opposite direction is a minus pi r square multiplied with the pressure plus the pressure with the distance away from this left hand side force, okay. So it's in the opposite direction from the x coordinate, so that's why it's negative. And then we have this shear stress acting in the opposite direction, which is against the x direction. So we have 2 pi r is the perimeter of the cylinder, and then we multiply with the distance dx, so we get the area, okay, of the cylinder, and then we multiply with the wall shear stress, then we get the force resulted by the wall, and then we equals to the 0, okay. So we simplify this equation, we'll get the pressure gradient the pressure gradient in the directions of x equals to negative 2 tau w. Tau w means tau of the wall, okay, and then divided by r. All right, so we can write this equation here. So this is how this equation being developed, okay. So from this equation we can try to solve for the we try to determine the velocity profile in the radius, okay, in the radius of the pipe. What can we do? We try to solve it, and by doing integration, and then we will get this velocity profile profile as a functions of radius equals to r squared divided by 4 mu. Mu is a dynamic viscosity, multiply with the pressure gradient in the x direction, and plus C1 ln r plus C2. So C1 and C2, they are unknown variables. So this unknown variable can be taken out if we know the boundary condition. So we pick two boundary condition. So one boundary condition is that at r equals to 0, r equal to 0 means at the middle of the pipe, the du dr, so the velocity du dr equals to 0. And then at another boundary condition is that at small r, the radius at r at the wall, so the velocity is 0, because we can see that the velocity of the fluid particle near the wall is basically can be assumed 0. Okay, so we have a velocity 0 at the wall of the pipe. Okay, so we use these two boundary condition, try to solve this equation, and this equation is coming from this equation. All right, so we try to solve it, and then we get this equation. Okay, so this equation is after solving this equation. So this equation, you can see that the C1 and C2 has been taken out because we have these two boundary condition. Then we can simplify this equation from here to here. So the unknown variable has been removed. All right, so if you remember about this average velocity that I shown to you a few slides before, average velocity. Okay, let's look at the average velocity. Okay, so the average velocity in the pipe, okay, is given by 2 divided by r square, integration from 0 to r on the velocity profile, velocity as a function of radius, multiplied with the radius and a differential of the radius. Okay, so with that equation, we just rewrite it here, and then now we know the velocity as a function of radius. We already have it here, we already determine it, so we can place it into the equation, and then we try to do integration from 0 for the radius from 0 to r. Alright, and then we get a minus r squared over 8 mu, 8 dynamic viscosity value, and then multiply with the pressure gradient dp dx. Alright, and then with this, if you look properly, how to say it, if you see properly, so this term is somehow similar to the term here. So we can rearrange this equation and placing this velocity as a function of radius into this part, and then we will get this equation. Okay, so this equation is a velocity profile. It's obtained from combining this equation with this equation. All right, so we get this. So I think this is not correct. So when r, so when r is equal to 0, when r is equal this r, when this r is equal to 0, you will get u max. Okay, u max equals to 2 multiplied with average velocity. So the average velocity is actually half of the maximum velocity in the center of the pipe. Okay, so here it's not r equals, it's not small r, it's not the radius equals to the r, it's a radius equals to 0 in order to get this equation. And then of course this equation can be simplified further, because we know that u max equals to 2 v average, so we just take 2 v average equals to u max. Okay, so we can rewrite the equation in this form. So apart from getting this a chance to estimate this average velocity from maximum velocity, so we also find something useful from this the average velocity relationship. Okay, so this V average equals to R negative R square over 8 mu multiplied with the pressure gradient, okay, dP dx. So this equation we can use it to derive the pressure head loss, okay, or the head loss. Okay, so pressure drop or head loss, okay, pressure drop and head loss, a quantity of interest in the analysis of pipe flow. In the pressure drop, okay, change of P, since it is directly related to the power requirement of the fan or pump to maintain flow. So if you have a pressure drop, if you have a head loss, means more energy is required to maintain the flow. Okay, so we note that dP dx equals to constant, and integrating from x x equals to x1, where the pressure is P1, to x equals to x1 plus L, where the pressure is P2. So it gives this kind of relationship. All right, so we take that equation, V average equals to this relation, okay, equal to this relation, and then we can write it here. All right, so we know that dP dx is equals to P2 minus P1 divided by L. L is just the horizontal distance or the length of the pipe that we are interested for comparison between point 1 and point 2. And so for laminar flow, okay, so we take the difference of pressure P1 P2, okay, is equals to, so 8 mu multiplied with the L, okay, multiplied with the L and multiplied with the velocity average divided by the R square, okay, divided by the R square. So you see here the negative cancel out because originally it's P2 minus P1. Now it becomes P1 minus P2, right? So we change the R square become D square, from radius become diameter, we get 32 mu L multiplied with the average velocity, okay, divided by D square. So a pressure drop due to viscous effect represent an irreversible, okay, it represents an irreversible pressure loss. And okay, a pressure drop due to viscous effect represent an irreversible pressure loss, okay, and it's called pressure loss change of PL. Okay, so we can actually write this relationship as changes of pressure loss. Okay, the pressure loss equals to F, which is given the name as a friction factor, multiply with L over D. D is the diameter of the pipe, L is the length of the pipe, and rho is the density, fluid density, and V average square over 2. Alright, this is the pressure loss for all types of flow developed internal flow. Okay, so PV square average over 2 is a dynamic pressure. The F is the Darcy friction factor, is given by 8 shear stress of the wall over the rho V average average velocity square. Okay, and then this this F thing can be written as 64 mu divided by rho D V average, can be simplified to 64 Reynolds number, because rho VD over mu is a Reynolds number, and this simple relationship is useful for circular pipe and laminar flow. And for this pressure drop, okay, pressure loss can also be simplified into HL, which is head loss. HL is a head loss by simply take this this term, this variable divided by rho L. Okay, because P equals to rho GH. So if you want to find the H, you just divide the P with rho G. So if you divide with rho G, you get something like this. HL equals to friction factor multiplied by L over D V average square over 2G. Okay, so in laminar flow, the friction factor is a function of Reynolds number only. Okay, and is independent of the roughness of the pipe surface. So the head loss represents the additional height that the fluid needs to be raised by a pump in order to overcome the frictional loss in the pipe. So this head loss is used to indicate the loss of energy. So whatever is lost, you need to accommodate for that. So you need to increase the pumping power in order to compensate for the loss due to the friction effect of the pipe wall, okay, or the friction loss. So we have determined the head loss, okay, from the pressure loss to the head loss. So we know that if we know the head loss, if we multiply the head loss with the mass flow rate and the gravity, so we can actually get this what's the power requirement to overcome this head loss. All right. So and this mass flow rate is given by rho v dot. Okay, so this is the volumetric flow rate. Okay, so you can see that rho g h is actually the pressure, so you get a pressure difference here. Okay, and then from the previous slide we show that the average velocity is equals to this relationship. So if this relationship can be rewritten, you'll get a different pressure multiplied by r square. Okay, different pressure multiplied by r square over 8 multiply dynamic viscosity and L. Okay, 8 multiplied with dynamic viscosity and L. L is the length of the pipe. So you can change the r square to d square from radius to diameter. You get this equation, and then simplify this P1 minus P2 as a changes of pressure. You get this. This is true for horizontal pipe, and we know that the volumetric, you can also write it for volumetric flow rate. You just multiply the average velocity with the area, okay, the area of the pipe. So simply change this equation to this, okay. So you get changes of pressure pi d to the power 4 over 128 dynamic viscosity and the length of the pipe. So this is Poiseuille's law. Okay, so we already have the equation for pressure loss, okay, and the head loss. All right, and the relationship pressure loss and head loss is one of the most general relation in fluid mechanics, and it is valid for laminar or turbulent flows, circular or non-circular pipe, and pipes with smooth or rough surfaces. Alright, so for a specific flow rate, so for a constant flow rate, the pressure drop and thus the required pumping power is proportional to the length of the pipe. So if you have a longer pipe, you will need you will have a greater pressure drop, okay, and you need also more pumping power. Now if your fluid that flowing through the pipe is large, so your pressure drop is also large, therefore your pumping power is also large. But if you increase the diameter, of the pipe by twice, you can actually reduce the pumping power by 16 times. Okay, so this is the example that show you the relationship between pressure loss, the pressure drop with increasing that indicates the required pumping power in relation with the length of the pipe and the viscosity of the pipe and also the diameter of the pipe. So if you increase the length of the pipe, you get more pressure drop, more power required. If you increase the viscosity of the fluid, therefore you have more pressure drop, you have more pumping power required. But if you increase the diameter of the pipe, you reduce the power requirement to push the fluid through the pipe. So we have discussed about the pressure drop or the head loss in a relationship with the length of the pipe and the viscosity of the fluid, and also the inverse relationship with the diameter of the pipe. It's time to look into the mechanical energy equation, okay, or the energy equation. Okay, so see how they can be actually how this energy equation can be transformed into the head loss and the pressure difference. So the head loss and the pressure drop, right? So first look into this energy equation. okay, as we been frequently shown to you before. So you can see that we have a pressure P1, P2, and also head loss, okay, apart from this velocity, elevation, H pump, and H turbine. So in order for this pressure difference to be equals to HL, so we need to cancel out many different terms in the equation, in the energy equation term. Alright, so let us try to understand how is that possible. So the pressure drop changes of P equals to the pressure loss changes of PL in the case of the horizontal pipe. But this is not the case for inclined pipe. Okay, inclined pipe means a pipe that is tilted, okay, or a pipe with a variable cross-sectional area. Okay, so this can be demonstrated by writing the energy equation for steady, incompressible, one-dimensional flow in terms of head as this following equation. Okay, so we wrote a Bernoulli equation, okay, with a correction of the velocity profile alpha 1, alpha 2. We have a H pump, we have a H turbine, and also a head loss. So head loss account for major head loss as well as minor head loss. And remember, we also have this pressure, energy, velocity, pressure, velocity, and also elevation. Okay, elevation head. So to make this equation similar to the pressure drop, okay, pressure drop equation, so we notice that certain terms has to be cancelled out. So okay, let us look into this. Therefore, the pressure drop changes of P equals to P1 minus P2. So we can rearrange this equation into the equation below here. So from there, we can see that the pressure drop P1 minus P2 and the pressure loss changes of PL equals to rho GH, right? So changes of pressure equals to the head loss. For a given flow section are equivalent, so we will get an equivalent like this only if the flow section is horizontal, so that there are no hydrostatic or gravity effect. So Z1 must be equal to Z2, so that we can cancel out this term. And then second, the flow section does not involve any work devices such as pump or turbine, since they change the fluid pressure. So the H pump and H turbine should be 0. So there should be no H pump, no H turbine, no H pump. Alright, so they should be cancelled out. And then third, the cross-sectional area of the flow section is constant, and thus the average flow velocity is constant, means that V1 equals to V2. So there's no change in the cross-sectional area. So V1 and V2, they are the same, so they can be cancelled out. So of course, number 4, the velocity profile at section 1 and 2 are the same shade, so alpha 1 equals to alpha 2. Alright, so means that this V1 equals to V2 and then alpha 1 equals to alpha 2, means that this kinetic head can be cancelled out. So after that, we cancel out the kinetic energy, cancel out the gravity effect, cancel out H turbine, cancel out pump. Therefore, we have the changes of pressure equals to head loss. So the equation that we derive shown to you, so it's a very special case. With all this condition meet, so we can actually convert the energy equation to pressure loss and head loss determination. Okay, so just now we developed this what I call velocity profile equation, okay, and the average velocity for this horizontal flow for fully developed laminar flow in a circular pipe. By using this method, now we want to use the same method also to derive the velocity profile in relation to the radius of the pipe, and we also want to determine the average velocity. Okay, so we want to do that for inclined pipe. Okay, inclined pipe. So now we use the same method, and now we want to do it for inclined pipe. So this is the effects of gravity. So once the pipe is inclined, we will include the effects of gravity. So the effects of gravity on velocity and and flow rate in laminar flow. So the pipe is inclined with theta degree from horizontal. So this is a free body diagram of a ring-shaped differential fluid element of radius r. So fluid element of radius r with a thickness of dr and the length dx. Okay, the length is dx, oriented coaxially with an inclined pipe in fully developed laminar flow. Alright, so we use the same balance of force. So we will develop this velocity profile in relation to the radius of the pipe. Now you see that for horizontal pipe, we get this equation, but with inclined pipe we have additional term. This is which is rho g sine theta. Okay, in the pressure gradient bracket. Okay, so if we do the same thing to estimate for the average velocity, we will get this equation. So we have a rho gl sine theta, and then if we want to convert it average velocity into volumetric flow rate, we will have this equation. Okay, so this slides shows the laminar flow in circular pipes. Is a fully developed flow with no pumps or turbine in a flow section. So the purpose is to know the head loss, the pressure difference in the pipe, and then we can estimate the what we call volumetric flow rate. Okay, as a result of this friction loss. So if you have a horizontal, you will have this equation, and if you have this inclined pipe, you would have this equation. Notice that we have a sine theta for inclined pipe. So if it's going up here, we have a theta greater than 0. So the sine theta will be greater than 0. So if it's down here, the theta will be less than 0. So the sine theta value will be less than 0. So the relation developed for fully developed laminar flow through horizontal pipe can also be used for inclined pipe by replacing the difference of pressure with this difference of pressure minus rho gl sine theta. Okay, so we just replace the difference of pressure with this. So this allows us to estimate the volumetric flow rate through the circular pipe under laminar flow in the presence of head loss. Okay, this slide shows the laminar flow in non-circular pipe. Okay, of course we have circular pipe as well as non-circular pipe. So the friction factor F relations are given in table. This is table 8.1 for fully developed laminar flow in pipes of various cross section. The Reynolds numbers for flow in these pipes is based on the hydraulic diameter dH equals to 4 AC divided by P, where AC is a cross sectional area of the pipe and P is the wetted parameter. So you can see you have A and B. So of course for circular, A and B will be non-available. So the friction factor is equals to 64 over Reynolds number. For rectangular, you have A and B. So if A divided by B is equals to 1, you have a 56.92 over R over Reynolds number for the friction factors. So if you increase this A over B ratio, you get an increase of this friction factor. Alright, so you not only circular, rectangular, we also have for ellipse and isosceles triangles. Okay, so this word isosceles is rarely came across. So this is pronounced as isosceles triangles. Okay, so now we are looking into the example 8.1 laminar flow in horizontal and inclined pipes. So this is horizontal and these are inclined pipes. Okay, so consider the fully developed flow of glycerin. Okay, glycerin at 40 degrees Celsius through a 70 meter long pipe. Okay, so L is 70 meter. Okay, all right. and then we read through the diameter is 4 centimeter. So diameter is 4 centimeter, okay, which is equals to 0.04 meter, okay, 0.04 meter. And then is a horizontal circular pipe. If the flow velocity at the center is measured to be 6, so the U max is 6 meter per second. Alright, 6 meter per second. Okay, and then 6 meter per second, and then we are asked to determine the velocity profile and the pressure difference, okay, across the 70 meter long section of the pipe, okay, and also to determine the useful pumping power required to maintain the flow. Alright, so this is the first part of the calculation. So we need to find UR. So what is the new UR? And then we need to find I think visibility is not so good, so let me try to enlarge it so that we can have a good view. Okay, we need to find the what I call velocity profile, the pressure difference. Okay, the pressure difference. What is the pressure difference? And then we need to know also the pumping power requirement. Okay, the pumping power. Okay, the pumping power required. Alright, what is the pumping power required? So if we look back to the slides, we could see that UR is equals to 2 V average, velocity average, in the bracket 1 minus R square over the radius, okay, the radius of the pipe square. Alright, so with this what we need to do is we can also convert this into U max. Okay, we can convert it into U max in bracket 1 minus small r square, the radius, small r square over big R square. Okay, and then we know the U max is 6, so we have 6 1 minus R square, and the R the big R square is actually 0.02 square. Alright, and then if we expand it, you get 6 1 minus 2500 small r square. Alright, so this is the relationship. Okay, this is the velocity. Okay, the velocity is that the velocity profile. Alright, and then we have to find the pressure difference. Okay, to find the pressure difference, we can actually write Bernoulli equation, compare two different point 1 compare with 2. Okay, so 1 and 2. Alright, so to compare this, we write the Bernoulli equation. Okay, we write the Bernoulli equation. H pump P2 rho G V2 2G Z2 H turbine. So from here we can cancel out the velocity. We know that in the horizontal pipe, okay, in the horizontal pipe, the velocity, how to say it, the velocity in the pipe is the same for equal diameter of the pipe. So for this reason, the V1 can be cancelled out. Similarly, for V2 can also be cancelled out. So in this case, initially we assume there's no pump, no turbine. Okay, so with that we can start to estimate what is the pressure. Alright, what is the pressure difference, right? So we want to estimate what will be the pressure difference. So pressure difference will be given by P1 minus P2 equals to rho G Z2 minus Z1 plus head loss. Okay, head loss. So pressure difference equals to, okay, so we have some missing information. So knowing that this liquid here flowing in the pipe is a glycerin, so the density for glycerin is what is the density for glycerin? 1252 kilogram per meter cube. Okay, at 40 degrees Celsius. So the the dynamic viscosity is 0.3073, okay, 73 kilogram over meter over second. This is also at 40 degrees Celsius. And then what else? Yeah, we know that the Umax is given as 6. So if you want to find the V average, velocity average, we take Umax divided by 2, so you get 6 divided by 2, you get 3 meter per second. Alright, so with this information we can calculate the Reynolds number. Alright, we can calculate the Reynolds number. Reynolds number is given by rho V average, diameter of the pipe, over the dynamic viscosity. Alright, so this would be given by the Reynolds number will be given by the 1252 kilogram per meter cube multiply with the average velocity, which is 3 meter per second, and then the diameter of the pipe, which is 0.04 meter, divided by the dynamic viscosity, which is 0.3073 kilogram per meter per second. Alright, so the Reynolds number would be 488.9. Okay, 488.9. So with the Reynolds number, now we can use the Reynolds number to calculate the friction factor. for the case of what we call laminar flow. Okay, laminar flow. Alright, so the friction factor equals to 64 divided by Reynolds number. So 64 Reynolds number will be 488.9. So 64 over 488.9 is 0.1309. So now we can estimate the head loss. Head loss will be given by this equation. Okay, friction factor, the length of the pipe over diameter of the pipe, velocity average square over 2g. Alright, then we have 0.1309. The length is what is the length? The length is 70. Okay, the length is 70 meter. So 70 meter over diameter is 0.04 meter. The average velocity is 3 meter per second square over 2 gravity 9.81. Okay, let me see. Oops. See if I can move it down a little bit. So we could write down the answer for head loss. So the head loss would be 105.1 meter. Alright, so now we can calculate the pressure difference, because we have this information. Okay, so before we do that, there's one more thing we can do. We can also calculate the volumetric flow rate. Okay, volumetric flow rate equals to AC multiplied with V average, velocity average. So the A is pi d square over 4, and V average, and this is given by pi d square is 0.04 square over 4 3. Okay, so you get the value of 377 multiplied with 10 to the power negative 3 meter cube per second. Alright, so we continue the pressure difference calculation. So we know the density, which is 1252 kilogram per meter cube, gravity 9.81 meter over second square, and then here Z1 Z2 will be 0 because it's horizontal pipe. Okay, horizontal pipe. And then the HL, the head loss, here we have 105. Here we have this value. Okay, we have this value 105.1 meter. Right, so it's 105.1 meter. So the pressure value, the pressure difference value, it will be 1290.6 kilopascal. Okay, alright, so this is the answer. Alright, And then now we can calculate the let me look the question again. Now we can calculate the pumping power required. So the pumping power is given by this equation. We pump the energy pump rate is pressure difference multiplied with volumetric flow rate. Alright, so the pressure difference here is 1290.6 kPa kilopascal multiply with the volumetric flow rate. We already calculate the volumetric flow rate as 3.77 multiply 10 to the power negative 3 meter cube per second. Alright, so the value would be 4.87 kilowatt. Okay, 4.87 kilowatt. Alright, so we try to look into the question again. Since we have this three answer, now if we look deeper, so we'll try to understand the question. For the same useful pumping power input, determine the percentage increase of the flow rate if the pipe is inclined 50 degrees downward, and the percentage decrease if it is inclined 50% upward. The pump is located outside this pipe system. So what happens is 50 degree upward and 15 degree downward. So we need to calculate what will be the we call increase or decrease of the flow rate. So we pick a case, then we conduct the calculation. So let's say we start with 15 degree upward. Okay, okay, 15 degree upward. So what we do, we calculate the pressure difference again, which is given by this equation. Okay, given by this equation, rho g, what we have is called Z2, but this is kind of slightly different because if 15 degree upward, we need this length. Okay, we need this length. Alright, and we know that horizontally there is a degree, right, which is 15. We know that initially it is horizontal, but now it is moved upward. Alright, so we want to estimate the Z2 minus Z1. Okay, Z2 minus Z1 plus head loss. Alright, so now the Z2 minus Z1, okay, so the Z1 is somewhere here, Z1, and the Z2 is here. Alright, so the difference of this height will be given by this L sine theta, okay, plus head loss. Okay, so this is the vertical. L sine theta is a vertical distance. Okay, so we try to calculate rho g. What is a rho g? It's 1252. Okay, G 9.81. L is 70 and theta is 15 degrees. HL already known, 105.1. So the value is 1513.4 kilopascal. Right, so now we have this. We want to find the flow rate. All right, so assuming that the pumping power is constant, now what happened to the flow rate? So the flow rate be given by W dot pump divided by the pressure difference. Okay, so this is 4.87 kilowatt divided by 1513.4 kilopascal. So we have 3.218 multiply 10 to the power -3 meter cube per second. So you see 4.87 we already calculate, we already know this is the pump power. So now we want to know if we move the pipe upward 15 degrees, what happened? If we still maintain the same pumping power, what happened to the flow rate? The flow rate has to decrease. Alright, it has to decrease. So the percentage, okay, the percentage decrease of the flow rate will be given by 3.218, okay, multiply 10 to the power -3 minus 3.77, the original volumetric flow rate, okay, 10 to the power -3, and divided by 3.77 multiply 10 to the power -3 multiply with 100, so the value will be -14.6%. So the flow rate dropped by 14.6%. Okay, so if we proceed further, now we want to work on downward 15 degrees. Oops. So 15 degrees downward. So similarly, find the pressure difference given by rho g. This time is negative, okay, negative L sine theta, because it's moving downward, plus head loss. Right, so it's 1252 multiply 9.81 in the bracket -70 sine 15 degree plus 105.1. Therefore the pressure difference will be 1068.3 kilopascal. Right, so maintaining constant pump power. Okay, so the volumetric flow rate, the new volumetric flow rate will be given by this equation. Okay, 4.87 kilowatt divided by the pressure difference that we just calculated, 1068.3 kilopascal. So we will get 4.559 multiply 10 to the power 93 meter cube per second. Alright, so the pressure, the percentage change in the volumetric flow rate will be given by 4.559 multiply 10 to the power negative 3 minus 3.77 multiply 10 to the power negative 3 divided by 3.77 multiply by 10 to the power negative 3 multiply with 100, and you will get 20.9%. So this is positive, okay, positive increase. Alright, so that's all for this question calculation solution. Alright, so 8.5, now we look at turbulence flow in pipes. Most flows encountered in engineering practice are turbulence, and thus it is important to understand how turbulence affects wall shear stress. Turbulence flow is a complex mechanism dominated by fluctuation, and it is still not fully understood. So we must rely on experiment and the empirical or semi-empirical correlations developed for various situations. So here is the figure. We have example A and B. Example A show the arrangement of the fluid particles before turbulence, and the picture B shows the arrangement of fluid particles after turbulence flow. So the intense mixing of turbulence flow brings fluid particle at different momentums into close contact and thus enhances momentum transfer. So turbulence flow is characterized by disorderly and rapid fluctuation of swirling regions of fluid called eddies throughout the flow. So eddies is like a spinning, okay, or something like a rotational flow. So these fluctuations provide an additional mechanism for momentum and energy transfer. In turbulence flow, the swirling eddies transport mass, momentum, and energy to other regions of flow much more rapidly than molecular diffusion, and greatly enhancing mass, momentum, and heat transfer. As a result, turbulence flow is associated with much higher values of friction and heat transfer and mass transfer coefficient. There are three figures here. So figure A shows the laminar flow, figure B shows a turbulence flow at high flow rate. So A is a laminar flow at low flow rate, B is the turbulence flow at high flow rate, okay, and figure C is also turbulence flow, but we have a shorter shutter exposure. So it means we expose the sensor of the camera to capture this flow at a shorter time of exposure. But for this one, the sensor of the camera exposed in capturing this flow at a longer shutter time. Okay, so this one is a shorter shutter time. Okay, that related to turbulence flow, but in particular relating to the details. So we will just skip this part and skip this part, skip these slides. We also will skip this, and also skip this. Alright, this is also excluded. Okay, now we get into the part that we want to talk about. That is the Moody chart and the Colebrook equation. Remember when we talk about the friction factor? So this friction factor can be determined by using a Colebrook equation. Okay, so this is for smooth and rough pipes. So for both smooth and rough pipe, we can use Colebrook equation to determine the friction factor. So friction factors can also be determined by using Moody chart. So it depends on whether you want to use Moody chart or you want to use Colebrook equation. But one thing for sure is if you use the Moody chart, you will have to find the friction factor F by using the chart. But if you're using Colebrook equation, then you might have to do some kind of iteration work. So if you look at this equation, which is for turbulence flow, you can see that there's a friction factor F appear on the left side of the equation and also on the right side of the equation. So there's no easy way to determine the F because it appears at two sides. So the method that they use to determine the friction factor F is to do iteration. So you have to calculate this equation several times until you get a converged value of the F. Means the F value will stay constant. Okay, so it's hard for me to explain to you how that works, but when there is an example, so you will see that clearly, right? So and the friction factor is in a fully developed turbulence pipe flows depends on the Reynolds number and the relative roughness, which is given by epsilon divided by the diameter of the pipe. There is also an explicit method. So if you don't want to use Colebrook method, there is an explicit method called Hallen equation to estimate the friction factor. But keep in mind that this explicit method, the accuracy may not be as good as the Colebrook equation. Okay. So if you look at the Colebrook equation, there is epsilon divided by d, which is the relative roughness. You can also see that this roughness epsilon is given has a different value given by different materials of the pipes. So this table shows the equivalent roughness value for new commercial pipes. So different materials of the pipe might have give different values of the roughness. Okay, and different relative roughness would give different value of friction factors. So the friction factors is minimum for smooth pipe and increases with roughness. So this figure shows the Colebrook equation again. So the Colebrook equation is implicit in F, since F appears on both sides of the equation. So it must be solved iteratively. Iterative means that you have to repeatedly solve for the F value, alright, or numbers of times, maybe 3 times, 4 times, 5 times, depending on your initial guess of the F value. Okay. So here is the Moody chart. Okay, the Moody chart, you can see that at the bottom you have Reynolds number. Okay, so you have to calculate the Reynolds number before you can use Moody chart. You also need the relative roughness given by the epsilon divided by the diameter. Keep in mind that if you have different, if the pipe is made of different materials, you will have a different relative roughness because you will have a different roughness value. So when you combine the Reynolds number and with the relative roughness, hence you can determine the Darcy friction factor F. Alright, so it appears that the roughness is given here. So if you look here, if the pipe is made of glass or plastic, the roughness is 0. Okay, so you get 0 value, and this roughness appear relatively high when this pipe is made of concrete. So concrete, you have a relatively high roughness value. And then if you look here on this Moody chart again, you could see that a line shows the laminar flow. So remember that in many previous slides we talked about the friction factor for laminar flow, which is equals to 64 over Reynolds number. So that gives us a straight line. So I think it's less than 2300 Reynolds number. You will fall within the laminar flow. Okay, so when the Reynolds number is between 2300 and 4000, then you fall within this transitional flow region. So in the transitional flow region, there's no easy way how you can determine the friction factor. But when it is greater than 4000 Reynolds number, then the flow in the pipe will be a turbulence flow. Alright, so I think the most important thing about the Moody chart is that you must learn how to read from the Moody chart when you have a Reynolds number and the relative roughness. So always keep in mind that the Reynolds number is always when you know your Reynolds number, you just draw a vertical line, and then when you know your relative roughness, you have to draw. Initially, you will have to draw a horizontal line that is parallel to the red horizontal line here, and then you have to follow this red horizontal line, and after passing through this dash line, okay, after passing through this dash line, right, so at a lower Reynolds number, this red line appears to curve upward, right? So take for example, here you have a 0.002 relative roughness, so you have to follow this red line, okay, then moving upward, following this curving upward red line, and this red curved line going up is referring to 0.002, okay, relative roughness. So if you have a relative roughness of 0.3, if you have a relative roughness of 0.003, so it will be in between 0.002 and 0.004. So 0.003 is somewhere here, so you have to follow this horizontal line and in the middle, and then as it curves upward, you also have to curve upward as well. So you have to follow this the space between them, okay, so it will be the middle going up. So if you have a Reynolds number somewhere here, then you have to draw a vertical line until your vertical line matches the relative roughness. So if your relative roughness is even smaller, let's say somewhere here, okay, somewhere in this line, okay, your your Reynolds number somewhere here, therefore from 0.003 we have to draw the line, and straight, it is horizontal line initially, but as it passes through the dash line, you have to move out according to the curve, so until it touches, then this is where the matching point is. Then only you draw a horizontal line to the left, then you will find your Darcy friction factor. Alright, so I think I will show an example how this can be done, that you can read from this Moody chart. Okay, so at the bottom we have a Reynolds number. Now we try to read this Reynolds number. So here we have 10 to the power 3. So this is 1000 Reynolds number, and here is 2000 Reynolds number, 3000 Reynolds number, 4000, 5000, 6000, 7000, 8000, 9000, and 10,000. Here is 20,000, 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, and 100,000 Reynolds number. Okay, then we have 200,000 Reynolds number, and so on. Okay, so that's how you read this Reynolds number. Imagine you have a relative roughness of 0.003, 0.003. So 0.003 is somewhere here, okay, somewhere in the middle between 0.002 and 0.004. Alright, so you draw a horizontal line and then you meet with the Reynolds number. Here, as an example, we pick 3 multiplied with 10 to the power 6, so it's somewhere here. So you draw a vertical line where the Reynolds number and the relative roughness meet. So once they meet, you draw another horizontal line from the right to the left where you will find the Darcy frictional factor. So in this case, you can roughly estimate it as 0.025. So the friction factor will be 0.025. Alright, so that's how you determine the friction factor. Here is another example that we would like to read from Moody chart. So in this case, we maintain the relative roughness as 0.003, and then the Reynolds number, we reduce it to 25,000. Okay, we reduce the Reynolds number to 25,000, and now we want to find the Darcy frictional factor. So it appears that the horizontal line from 0.003 from the relative roughness will meet the this dash line, and then after that the curve appears to be moving upward, so we have to follow this curve moving upward, alright, until it meet with 25,000 Reynolds number. So once it's meet, once the Reynolds number and the relative roughness meet, we can draw a horizontal line from the right to the left, and that is where we find the Darcy frictional factor. So in this case, in this example, we found the frictional factor as 0.03. So here is the difference when you have a curve that moving upward. So we have to follow the curvature of the curve going up in order to find the friction factor. So here is the observation from the Moody chart. For laminar flow, the friction factor decreases with increasing Reynolds number, okay, and it is independent of surface roughness. So for laminar flow, okay, here, so what happened is that when we increase the Reynolds number, okay, when we increase the Reynolds number, the friction factor reduces, okay. When we increase the Reynolds number, the friction factor reduces in the laminar flow. The friction factor is a minimum for a smooth pipe and increases with roughness. Okay, the Colebrook equation in this case, when the epsilon, the roughness, becomes 0, reduces to the Prandtl equation. So when epsilon becomes 0, you get Prandtl equation. The transition region from the laminar to turbulence region, okay, from laminar to turbulence regime, is indicated by the shaded area of in the Moody chart. So here's a shaded area, okay. At small relative roughness, the friction factor increases in the transition region and approaches the value of smooth pipe, okay. At a very large Reynolds number, to the right of the dash line on the Moody chart, the friction factor curve corresponding to specified relative roughness curve are nearly horizontal, and thus the friction factors are independent of the Reynolds number. So you see this dash line, alright, so at a large Reynolds number, we can see that Darcy friction factors correspond to the relative roughness after this dash line. Okay, so this happened in a fully rough turbulence flow region. Okay, so this is what we get at a very large Reynolds number. The friction factor curve correspond to the specified relative roughness curve are nearly horizontal, and thus the friction factor, okay, are independent of the Reynolds number. So the flow in that region is called fully rough turbulence flow. So these are the region of fully rough turbulence flow. The Colebrook equation in a fully rough zone reduces to von Karman equation. So this is the equation you get for this fully rough turbulence flow region. So when we try to calculate this relative roughness, we know that it is consists of the roughness value divided by the diameter of the pipe, right? So in the calculation, we should make sure that we use the actual internal diameter of the pipe, which may be different than the nominal diameter. So in the industry, they stated that there is a nominal size. So nominal size is not represent the actual size, it's nearly the actual size of the diameter. So we must always use the actual inside diameter, whether it is inch, feet or millimeter. Alright, so if our epsilon is in feet, make sure that our diameter is in feet. If our epsilon is in millimeter, make sure that our diameter is in millimeter. So we don't use nominal size, we use the actual inside diameter. Alright, so for example, you say in the nominal size of 5 inch, the actual inside diameter is 5.047. So, right, so make sure we use the correct actual inside diameter to estimate the relative roughness. Alright, so at a very large Reynolds number, this one we already mentioned before, the friction factor curve on the Moody chart are nearly horizontal, and thus the friction factors are independent of the Reynolds number. So they are independent of the Reynolds number at a very high Reynolds number. Okay, so the friction factor become independent. So at this very high Reynolds number, right? And there are a few types of fluid flow problem. So in a type 1, you will be given the length of the pipe, you will be given the diameter of the pipe, also the volumetric flow rate, and you are asked to find the head pressure loss or the head loss, right? So that is the type 1 fluid flow problem. The type 2 fluid flow problem is when you are given the length, diameter, and the pressure difference, the pressure drop or the head loss. Then you are asked to find the volumetric flow rate. And the type 3 problem is you are given the length, the volumetric flow rate, the pressure loss or head loss. You are asked to find the diameter of the pipe. So we have the 3 types of problem encountered in pipe flow. All right. So as you know, if you want to find this solution by using this Colebrook equation, so we need to do some iterations work. It means we have to repeated calculations to find the friction factor. To avoid this kind of trouble, there is also explicit equation. So here's the explicit equation. For example, you want to find the head loss, you can use this equation to find for the head loss in a type 1 problem. For type 2 problem, you can use this equation, and for type 3 problem, you can use this equation. And keep in mind that there is certain range where this equation is valid. So if you fall out from the range given here, then the estimation become invalid. Okay, so to avoid tedious iteration in a head loss, okay, head loss calculation, flow rate, okay, volumetric flow rate, and diameter calculation, so diameter calculation, these explicit relation, so here are the explicit relations that are accurate to within 2% of the Moody chart may be used. So the calculation from this equation, they may not be very accurate, but the accuracy is only within 2%. Okay, 2% error, okay, of the Moody chart. Here is the example 8.4, determining the diameter of an air duct. Okay, so the heated air at 1 atm, okay, at 1 atmospheric pressure and 35 degrees Celsius is to be transported in a 150 meter long circular plastic duct at a rate of 0.35 meter cube per second. So it's shown in this figure. If the head loss in the pipe is not to exceed 20 meter, so determine the minimum diameter of the duct. So what happened here is that you've been given the length of the pipe, which is 150 meter. You've been given also the flow rate, okay, the volumetric flow rate, okay, and also been told that the head loss should not exceed, okay, 20 meter. So the head loss is comparable to pressure loss because P equals to rho GH. Now you are asked to determine the diameter, okay, the minimum diameter of the duct, okay. So if you compare with the table, obviously it is a type 3, okay, type 3 fluid flow problem, okay, so it's a type 3. All right, and then based on the temperature 35 degrees Celsius for air at 1 atmospheric pressure, you can determine the density, okay, the density of the air, the dynamic viscosity of the air at 35 degrees Celsius, and the kinematic of the air at 35 degrees Celsius. So this problem can be solved by using Colebrook, okay, Colebrook equation. Okay, so this is the Colebrook equation. So we use this equation to solve the problem. So first we write out the Colebrook equation, and you can see that in the Colebrook equation we have a friction factor, we have a relative roughness with the roughness divided by the diameter of the pipe, and then we realize that this circular plastic duct, okay, so it's a circular plastic duct. So when it is plastic, okay, when it's plastic, the roughness value is 0. So 0 divided by the diameter, okay, you get 0. Therefore these terms become 0. So we can simplify the equation, we can simplify the Colebrook equation into this form. Then we are left with Reynolds number and the friction factor. Alright, so in order to find the Reynolds number, we need to write the Reynolds equation, rho Vd over dynamic viscosity. So the dynamic viscosity divided by density, we get the kinematic viscosity. So this is a kinematic viscosity. So the V is the average velocity, D is the diameter of the pipe, and this small v is actually the kinematic viscosity. So we can put in the kinematic viscosity for the air, because we know the kinematic viscosity. But then the velocity, okay, of the air and the diameter of the pipe we don't have, so we need to calculate the velocity. So we can write out the velocity equation, which is equals to the flow rate, volumetric flow rate, divided by the area. So the area is pi d squared over 4. So we know that the volumetric flow rate has been given as 0.35. So we can put in the volumetric flow rate, but the diameter is not given. Alright, and then back to Colebrook, the simplified Colebrook equation, and the F is a friction factor. We know that F is related to the what I call pressure loss equation, or the head loss equation. So the head loss, we know that should not be more than 20 meter. So we replace the head loss with the 20. And then the F is a friction factor. The length of the pipe is 150 meter. The diameter we don't know. The average velocity of the air we don't know. And then of course the G is the gravity. So end up we have 4 relations. We can solve this by guessing the initial value of the diameter and then iterate throughout the process and to find the F value. Okay, so once the iteration is complete, we will have a constant value for D, constant value for F, constant value for V, constant value for Reynolds number. So this iteration will take a few steps. So we will start with the initial guess of the D value. Alright, or we can also solve it using simultaneously, okay, by using some computer software. Or another method is to calculate it by using this explicit equation. So this is the explicit equation where we can use to solve the third type, okay, the third type fluid flow problem. All right. So if you solve it with the simultaneous solution, or the iteration method, you get the D of the diameter equals to 0.267 meter, F the friction factor 0.018, average velocity of air 6.24 meter per second, and then the Reynolds number of about 100,000. Okay, so if we find out that by using this kind of method is too complicated, there is an alternative method, as I mentioned to you. We can use this explicit method, okay, using this equation, and this equation is known as what we call they call it Swami-Jain formula. Okay, so this is a Swami-Jain formula. You can see there's an epsilon here, which is 0 because of the plastic, okay, of the pipe. So this term becomes 0. So you only left with this. Okay, so now the volumetric, the kinematic viscosity, we already know. Okay, we already know the kinematic viscosity value, which is we can find it from the table. And then this volumetric, okay, volumetric flow rate is also given, which is 0.35. The length is 150 meter. Gravity we know. Head loss is we want it to be not more than 20 meter. Okay, so seems like all this value for all these variable we have it, so we can calculate the diameter. So it turns out that the diameter is 0.271. So we can see that it is slightly greater than the method solved by using what I call by either iterative or simultaneous, what we call this simultaneous method. Okay, so this is slightly higher. It's not the same due to inaccurate equation. So as we know, the accuracy of this equation is only 2%. It has a 2% of error. Okay, all right. Here is example 8.5, which is extension of from the previous example. So the question now is the duct length is double. So we want to increase from 150 to 300 meter, and we maintain the diameter. Okay, so the diameter remain the same, which is 0.267, and then if the total head loss is to remain constant, so we do not want to increase the total head loss. So what happened? Determine the drop in the flow rate through the duct. So now we are asked to find the volumetric flow rate. So you know the length of the pipe, which is 300 meter. the diameter is 0.267, and the head loss or the pressure loss, the head loss is to remain at 20 meter. Now find the volumetric flow rate. So this obviously is a type 2 fluid flow problem. Okay, so so we'll try to solve these problems by using Colebrook equation. So we write out the Colebrook equation, and then from here, similarly, you can see that the epsilon becomes 0, the roughness is 0 because of plastic. So we have, you can simplify it here. Now we have Reynolds and a friction factor, which we want to determine. But the Reynolds, we can also write out the equation as this. So we have a velocity, diameter, and a kinematic viscosity. So we have kinematic viscosity. We have the diameter of the pipe, which is 0.267, but we don't know what is the velocity, and the velocity is given by Q over A. So we know we want to find the Q now. Okay, so we want to find the Q value. So but the D, the diameter of the pipe, we have it 0.267. And then if we look back into this Colebrook equation again, we notice that we have a friction factor. The friction factor is related to the head loss equation. So we know the head loss is remain 20 meter. We know the length is 300 meter, diameter 0.267. The velocity we don't know, and we have the gravity. So now we end up with 4 equations. Either we solve it by using iterative method, by initially guessing the volumetric flow rate, or we can also do simultaneously solve the equation using some software. So here, if you either method you use, you will end up with this value. Okay, so we have the volumetric flow rate 0.24, friction factor 0.0195, and average velocity 4.23 meter per second, and a Reynolds number of 83,000. Okay, and now we know that initially is 0.35 the air. Now the new value we get here is 0.24. So 0.35 minus 0.24, we have a difference of 0.11 meter cube per second. So that is a drop of 31%. So these slides show you the guessing, okay, the guessing value. So they solve this equation by first guessing the what I call friction factor. Okay, so they guess the friction factor, and then they calculate the velocity. Okay, then they calculate the velocity. Okay, alright, then they calculate the velocity. Okay, they guess the friction factor, so they estimate the velocity, and then they calculate the Reynolds number. So when you have V, you can calculate the Reynolds number, and then from the Reynolds number, you recalculate from the Reynolds number, you recalculate the F value. Okay, you recalculate the F value. Okay, so and then you use the same this F value you created, and you make it as a input again, and then you recalculate the whole velocity Reynolds number until you get a friction factor again. So from this friction factor, you repeat the same process again. So until in the end, you get a constant friction factor. Therefore, you could say that the friction factor is converged. So in this stage, you don't have to repeat the calculation anymore. If you repeat the calculation, you still end up with the same friction factor. So if you see here, they repeat the calculation 5 times. Okay, in order to get the convergent value for the friction factor. So once you get a convergent value for the friction factor, your Reynolds number is correct, your velocity value is correct. Okay, so this equation is an alternative method, okay, which is an explicit equation. So we just use this equation to calculate the volumetric flow rate. So for this example 8.5, apart from iterative solution, and the simultaneous solution, we can also use this what I call explicit equation to solve the problem. So we can determine the volumetric flow rate using the explicit equation, which is known as Swami-Zane formula. We know that this epsilon is 0, okay, because the roughness is 0 for plastic pipe, and we only have this term and this term for the calculation. So we just put in the variable we know, and then we calculate for the volumetric flow rate. So the volumetric flow rate is 0.24 meter cube per second, and it turns out to be similar to the iterative method as well as the simultaneous method. So keep in mind that this Swami-Zane formula may not always give you the accurate solution, but it's a good method to check your answer. Maybe you have an error of 2%. Maybe this formula sometimes can give you an error within 2% of accuracy. So in any case, you might also want to check your iterative solution or the simultaneous equation by using this I call explicit equation, just to cross-check your answer. So as long as you get a relatively near answer to the Swami-Zane estimation, therefore your iterative method must be correct. Okay. So now we look at minor losses. All right. So all those losses that heat loss, pressure loss that we've been talking about before this are major losses. Okay. Referring to the loss in the pipe, okay, in a long pipe. And now we have minor losses. So what are these minor losses? The fluid in a typical piping system passes through various fitting, valves, bands, elbows, teeth, inlet, exit, enlargements, and contractions in addition to the pipe. So apart from the long pipe that we've been talking about, the head loss, pressure loss, there's also this kind of fitting, okay, valve, bands, elbows, teeth, inlet, exit, enlargement, and contractions. So these kind of things causes cause minor losses. Okay, so these components interrupt the smooth flows of fluid and cause additional losses because the flow separation and the mixing they induce. In a typical system with long pipes, these losses are minor compared to the total head loss in the pipe. That is the major losses. And these fitting valve, bands, elbows, and etc. are called minor losses. Minor losses are usually expressed in terms of loss coefficient KL. Okay, so let's try to understand how these loss coefficient are being determined. So initially you have a pipe, okay, and you compare 0.1 to 0.2. So the pipe is horizontal, so you have a pressure 0.1 compared with a pressure 0.2. Alright, so you might ask the reason why we compare pressure. Because head loss appear in a pressure loss. Alright, so what happened here is that because of the major head loss, okay, major loss, you have a pressure drop, also pressure drop or head loss. Okay, and now you insert this valve, okay, in between this 0.1 and 0.2. Then this valve create another loss, that the loss caused by the valve. Initially you have loss, but the loss is a major loss caused by the friction in the pipe. So you have P1 minus P2 pipe. Okay, now you have the valve in between the pipe, in between the 0.1 and 0.2. So you have another loss. The loss is resulted by the valve. So with P1 minus P2 valve. So what happens is that if you take P1 minus P2 valve minus bracket P1 minus P2 pipe, so this additional loss, okay, additional loss caused by the valve, which is in addition to the major loss. Okay, So these are minor loss in addition to the major loss. So the loss caused by the valve in addition to the major loss, this loss is referring to the minor loss. All right. So why is that the case? Because you have major loss in the long pipe. That's before the installation of the valve, and then when you increase, when you add another valve, so this pressure loss further increases. Okay, this pressure loss further increases. Then you add another loss to the system. So this loss caused by the valve that is in addition to the major loss is called minor loss. So for a constant diameter section of a pipe with a minor loss component, the loss coefficient of the component such as the gate valve, so this is a gate valve shown, is determined by the measuring additional pressure loss it causes and dividing it by the dynamic pressure in the pipe. So we calculate here, we got this minor loss. So the minor loss, we divide by the rho g, we get this head loss. Okay, so the minor head loss. So this minor head loss, we divide with the dynamic, okay, the dynamic head of the fluid, we get this loss coefficient. So basically we have what we call the pressure loss divided by the dynamic head. Okay, so you get loss coefficient. So when so here's the figure shows in the case of band, okay, 90-degree band. So the fluid flow through the band. So so you have this kind of valve. Okay, so the head loss caused by a component such as the angle valve shown is equivalent to the head loss caused by sections of pipe whose length is equivalent length. So the loss here, you can try to find the loss caused by the minor loss. Okay, the minor loss, and you can make it equivalent to a horizontal length of the pipe without the valve. Okay, so when the inlet diameter equals the outlet diameter, the loss coefficient of the component can also be determined by measuring the pressure loss across component and dividing it by the dynamic pressure. So we divide by the dynamic pressure. So this is a minor loss. Okay, minor loss pressure divided by the dynamic pressure. So you get the what we call loss coefficient KL. Okay, loss coefficient KL. So when the loss coefficient for a component is available, the head loss for that component is, so you take the loss, you take the loss coefficient KL, multiply with the dynamic head, you get the head loss. Okay, the minor head loss. Okay, so the minor head loss, or in short, call it minor loss. The minor loss are also expressed in terms of equivalent length. Okay, L equivalent. So this minor loss is resulted from the band and also this angle valve. So if you want this length, this loss can be made equivalent to horizontal length loss. Okay, as a horizontal length of a pipe that create similar minor loss. Okay, that's what it means. So you take this head loss caused by the minor loss equivalent to the head loss equation. So you can see that this v squared over 2g can be cancelled out. Then you only left with loss coefficient and this equivalent length. Okay, equivalent length, this diameter and the friction factor. All right. So if you take the major loss plus the minor loss, then you get a total head loss. Okay, total head loss in the pipe. So major head loss, you know this pressure loss equation. Okay, so we can write down the pressure loss equation, which is depending on the length of the pipe, right? So you have a length of the pipe, diameter of the pipe, and also the velocity of the fluid, okay, and the friction factor. So you get the major loss. For the minor loss, you take this loss coefficient multiply with the velocity square over 2g. Alright, so if you combine these two, you get this total head loss equation, okay, where the d, the diameter, is a constant. So now is a good time to look into what are these major loss made of. What are these small changes that can cause some changes in the value of minor loss. So for example, if you have a sharp edge inlet, okay, so your loss coefficient is 0.5. So when you have this well-rounded inlet, and then you have a loss coefficient of 0.03. So it depends on the radius r over d, which is the diameter, right? So the head loss of at the inlet of a pipe is almost negligible for well-rounded inlet. So for well-rounded inlet, the loss coefficient is 0.03 for RD more than 0.2. So the greater the R value, the well-rounded the edge would be, the inlet edge would be. But it increases to about 0.5 for sharp edge inlet. So with a sharp edge, you get more loss coefficient. Why is that? Because well-rounded inlet has less friction. So this is a sharp edge, it has more friction. So this sharp edge create some kind of turbulence, okay, some kind of rotational flow somewhere after the inlet, okay. So and because of that, it reduces the flow area, okay, reduces the flow area, increases more friction. But well-rounded inlet does not create this kind of rotational flow of fluid particles after the inlet area. So that's why well-rounded inlet has a lower loss coefficient compared to the sharp edge inlet. Okay, the figure here shows the loss coefficient, okay, KL, which is the minor losses of various pipe components for turbulence flow for use in the relation of head loss equals to KL V square. V is the average velocity, KL is the loss coefficient, and of course divided by 2G, where V is the average velocity in the pipe that contain the component. Okay, so if you look at different kind of inlet and different kinds of exit, different kind of inlet, as we mentioned before, well-rounded, R over D greater than 0.2, you get a loss coefficient of 0.03. Okay, very small. But when this R over D equals to 0.1, then you get a higher loss coefficient, 0.12. So if you have a sharp edge, the loss coefficient will be 0.5. If you have a re-entrance, you have a loss coefficient of 0.8. It's even higher. Alright, so for pipe exit, the loss coefficient is the same for re-entrance, sharp edge, and also rounded. Okay, so also we should note that the kinetic energy correction factor alpha is 2 for fully developed laminar flow, and alpha will be 1.05 for fully developed turbulence flow. So this slides shows the sudden expansion and contractions based on the velocity in a smaller diameter pipe, and also gradual expansion and contraction based on the velocity in a smaller diameter pipe. So for sudden expansion, sudden contraction, we can see that for sudden expansion it follows this kind of formula, and then for sudden contractions it follows the figure here. Alright, so it seems like the larger the difference of diameter between the large diameter and small diameter, if the difference is large, then you have more friction. So if they become similar, then you have less friction, less loss friction, okay, less minor loss. That's what it means. All right. So in a gradual expansion and contraction, for expansion, when the small diameter becomes similar to the big diameter, you have less friction. So if the small diameter is largely different from the large diameter, means that the difference between them is large in terms of diameter, then you have a higher friction. I think the same for contraction. It will depends on the angle. So the angle, if the angle is big, then the friction will be big. When the angle is small, the friction will be less. So means that angle small means the diameter will be similar, nearly similar to one another. Okay. So if you have a larger angle, means the diameter will be largely different. Okay. Here are some additional bands and branches, also valve. So all these are minor losses. Okay, they create some kind of minor losses in addition to the major loss. Some things that worth mentioning is flange. Okay, so flange is this part. Okay, this part, it will join to a pipe, to a long pipe, either by flange or threaded. Okay, so flange is something like this. This is flange. Okay, flange. Okay, so this is also flange. Okay, threaded is like it's like a spinning. Okay, you have to spin to tighten the joint. Right, for flange you just need to use a nut to tighten the joint. For threaded, you need to spin the pipe until they join close to one another. For example, you want to open a bottle of if you want to open the cap of the bottle, you have to spin and open the cap of a bottle, right? So that is threaded. Okay, so the pipe and the band can join together either through flange or through threaded. So if it's threaded, you have more friction. If it's flange, you have lesser friction. So also keep in mind that if you have valve, different kind of valve also will give different kind of loss coefficient. That implies minor loss. Okay. So I think this diagram show a very good example of this threaded union. So threaded joint. So in order for the pipe to join, so you have to spin this pipe. Okay, you have to spin this. You have to twist, spin this pipe and into into the what I call the cap. Okay, so this is a threaded threaded union. All right. So sometimes here can also be threaded. Okay, so it depends depending on the design whether it's flange or threaded. Okay, the slide here shows the sudden contraction. Alright, so the graphical representation of flow, contraction, and the associated head loss at the sharp edge pipe inlet. So if you compare 3.0, 1, and 2. So initially we have a total head loss remain constant. Okay, but after this sudden contraction, after this after this entrance, after this entrance, you have a head loss. So that is a minor head loss, right, resulted by this sharp edge. All right, and then if you look at the velocity head, in point 1 is very high. Because why? Because there's a spinning of particles near the wall after the entrance, and then after that the velocity reduces. The velocity head reduces, but as a result of that, you have the what I call minor head loss. Okay, so the loss velocity head. Okay, so if you have a rounded edge, okay, you have a rounded edge for the entrance, the greater the R, so means that the more rounded would be for the entrance, the less friction you're going to get. Okay, the less friction you're going to get. So R, the higher the R over D ratio, the lesser the friction, means the lesser the minor loss. The slides here shows the if you have a submerged outlet, so the jet, okay, all the kinetic energy of the flow is lost, turned into thermal energy through friction as a jet. Okay, so we have a jet entering into this ambient fluid. So this so the jet decelerate and mixes with the ambient fluid downstream. So the jet fluid enter the ambient fluid and it mixes with the surrounding fluid, so cause it to decelerate. Okay, and because of that, there is loss. Okay, there is a loss. Okay, and another example is the loss during the change of directions. Okay, change of direction, for example 90-degree turn. So the loss during the changes of direction can be minimized by making the turn easy. So easy on the fluid by using circular arc instead of sharp turn. So this is a sharp turn and this is the arc. Okay, circular arc. Okay, so when you do that, you reduce the friction. That's why you have a low loss coefficient, which means low minor loss. Okay, when you have a sharp turn, then you have more disturbance, you have more turbulence flow, you have more friction. As a result, you have more loss coefficient, which implies high minor loss. Okay, high loss. Here we have the comparison between a globe valve and a ball valve. So both are in an open stage, but it turns out that this globe valve has more minor loss than a ball valve. The reason is quite simple. On the outside, it seems that the velocity before and after the globe valve is similar, but in a small area of opening here, which is the constriction area, the velocity is very high. So although V1 equals to V2, V2 equals to V1, but the V constriction area is very, very high. So this area causes what I call the fluid to decelerate. A small area causes the fluid to decelerate, means the fluid to slow down, and then we have mixing. Okay, mixing happening, and then once the fluid leave the constriction area, there is a flow separation and mixing as well. All right, so you have a flow separation and mixing cause loss. Okay, and if you look into this ball valve, the head loss through a fully open ball valve, on the other hand, is quite small. So the restriction area is not as much as the restriction area in the globe valve. So the ball valve is a better option in terms of less minor loss. So let us look into example 8.6. Okay, head loss and pressure rise during gradual expansion. So referring to this question, there is a 6 centimeter diameter horizontal water pipe. Okay, expand gradually into 9 centimeter diameter. So from 6 diameter, D1 is 6 centimeter becomes 0.06 meter. Then we have D2 diameter becomes expanded, become 9 centimeter, which is 0.09 meter. Then the wall expansion section is 10 degree. So here we have 10 degree. Here also have 10 degree. So total we have 20 degree. Okay, 10 degree. So you can look at this. Okay, so the angle has to be 20 degree. Okay, because we have 10 degree at the top, 10 degree at the bottom. And then let's look further. Average velocity. Okay, the average velocity and pressure of water before the expansion section is 7. So V1 is 7 meter per second. And then this P1 is 150 kilopascal. Alright, so determine the head loss. Find the head loss. Okay, and also find the head loss in the expansion section and the pressure in the larger diameter pipe. So P2, what's the value? So if you want to find HL, we know that HL, head loss, equals to the loss coefficient, right? Is it the loss coefficient? I think it's called loss coefficient. Okay, loss coefficient, yeah, correct. It's a loss coefficient. Alright, loss coefficient. So the loss coefficient, V1 square over 2G. Okay, so we need to find the loss coefficient KL. How do we find? So we look into here. You can take the diameter of small pipe over the big pipe after expansion. So the small diameter over the big diameter. So we must find where is it. Then only we can determine the KL. So what we do here is we find the D. Okay, so D1 over D2. Okay, so this is actually the D, small d over big D. Right, so what you get, 0.06 over 0.09. So what's the value? The value of the D ratio is 0.667. Alright, so 0.0667, so it's somewhere here. Okay, it is somewhere here. Alright, so let us calculate. We just list it out. Okay, so KL. So KL between 0.15 and 0.10, and then you have 0.6 to 0.8. Alright, so definitely this value is somewhere here, and then we need to find the KL value here. Okay, so what we do, we take KL minus 0.15 over 0.1 minus 0.15 equals to 0.667 minus 0.6, okay, divided by 0.8 minus 0.6. So the KL value will be 0.1333. Alright, so now we can calculate the head loss. Okay, we can calculate the head loss. So head loss 1333. V1 is 7 square and 9.81. Okay, so what's the value for this calculation? Let me see. the value would be 0.3329 meter. Alright, so now we want to find the pressure at point 2, right? Now how can we do? Just write the Bernoulli equation. Okay, you can use the Bernoulli equation, P1 rho g, V1 2g, Z1 H pump, P2 rho g, P2 rho g 2g, Z2 H turbine plus head loss. Alright, so I think we've forget one thing that is the quite important here. Here is alpha 1. Okay, put alpha 1, and here we also have another one. Okay, here is alpha 2. Okay, the correction for the velocity. So what we can do, we can try to cancel out, see which part is not needed. Okay, so appears that is horizontal, so Z1 will cancel out with Z2. There's no pump, there's no turbine. Alright, so we want to determine the P2. Okay, we want to determine P2. Now we can rearrange the equation. So P2 rho g equals to P1 rho g minus, okay, not minus, plus, okay, plus alpha 1 V1 2g minus alpha 2 V2 2g and minus head loss. Okay, minus head loss. So we can rearrange the equation where you get where we will get P1. Okay, okay, where we will get P1 plus rho bracket alpha 1 V1 2 square 2 minus alpha 2 V2 square over 2, okay, minus GHL. Okay, so notice that we don't know what is alpha 1. We also don't know what is alpha 2. Alright, we have the value for V1. We don't know what is V2. Okay, so what is V2? We have the value for H. We know what is the density of the water. We know P1. So we need to find out this answer. Okay, how can we do? We know there's a what I call conservation of mass flow rate. Okay, so we can use conservation of mass flow rate at point 1 compare with a conservation of mass flow rate at point 2. Okay, point 1 and point 2, we compare the mass flow rate, should be the same. So it will be rho A1 V1 rho A2 V2. That's why we get pi d1 square over 4 v1 pi d2 square over 4 v2. So obviously this one we cancel out, okay. right? And then now we can do cancel again. Okay, cancel again. Okay, so we want to find V2. So V2 will be D1 over D2 square V1. So D1 over D2. So D1 is what? D1 is oops, what is going on? Oops. I think we accidentally moved something. Anyway, I think I accidentally moved something here. Obviously here is yep. Okay, so here is D2. Alright, so this one must be D1 over D2, which is D over D. Alright, and then there's a 2 here to cancel out. It's only kilopascal. And then now I want to find okay, we continue. D1 over D2 is 0.06 over 0.09 square. V1 is 7. So the answer will be, what will be the answer? 3.11 meter per second, right? Okay, so now we have V2, and we want to find alpha 1 and alpha 2. If you look back, alpha 1, alpha 2, okay, so the alpha is 1.05 if it's a fully developed turbulence flow. Alpha will be 2 if it's for developed laminar flow. Alright, so which condition are we in now? So easiest way, let's find the Reynolds number. Okay, let's find the Reynolds number to justify our case. So Reynolds number 1, rho V1 D1 over kinematic viscosity, right? So rho is 1000, V1 V1 is 7, D1 0.06, and the dynamic viscosity is 0.891 multiply 10 to the power negative 3. So how do we know? We can check from the table. Okay, so at room temperature, because we are not given the what you call the room condition, so we can actually assume that it is at room temperature. Okay, at 25 degree. Okay, at 25 degree. at 25 degree. So here's 25 degree. The dynamic viscosity. So this is the dynamic viscosity. So let me enlarge it so you can see it clearly. So it's hard to enlarge. So it's not possible, but anyway, 0.891. Let me just show this quickly. Okay, at 25, let me show this. At 25 degrees Celsius, you get the what I call dynamic viscosity 0.891. Okay, multiply 10 to the power -3. This is for liquid water. Okay, liquid water. So let us continue. So now we want to calculate the value. Alright, 10 to the power 3 multiply 7 multiply 6 divided by 891, 10 to the power -3. So it's 4.7, 10 to the power 5. Definitely it's turbulence. Okay, because it's more than 4000 Reynolds number. So your alpha 1 would be, so we check back alpha 1 for turbulence flow 1.05. Okay, 1.05. Alright, so Reynolds number 2, rho V2 D2 and mu. This will be 10 power 3. V2 is 3.11. D2 is 0.09 and mu is 0.891 multiply 10 to the power -3. So what will be the Reynolds number? It will be 3.14 multiply 10 to the power 5. Okay, again turbulent. Okay, because it's more than 4000 Reynolds number. So alpha 2 will be 1.05 again. So now we have alpha 1, alpha 2 and V2. So we can go for this equation. Okay, you can go for this equation. Touch. Okay. Let's see. control V. Okay, done. All right. So we just place in what is P1. P1 is 150 kilopascal. P1 is 1 what is going on? Okay, 150. Okay, power 3, 150, 150,000 Pascal, plus the rho is 1000. So I don't show you the unit, but when you are trying to calculate, it's good that you practice key in all the units. Okay, write out all the units, because this will will avoid mistakes. Okay. Then the alpha 1.05. Then the V1 is okay. Then the V1 is 7 square over 2, 9.81 minus 1.05. Then the V2 is 3.11 square to 9.81 minus 9.81 HL head loss 0.3329. Okay, so did we key in everything correctly? Oh, I think we make a mistake here. There should not be a gravity here. Alright, should not be any gravity. Alright. So if you calculate, the value will be 167 kilopascal. Right? We can also write as 1. Okay. It is 1673000 Pascal. You can also write as 167 kilopascal. Alright, that's all. That's how you get the calculation done. So it's also good try to understand what's going on. So initially we have 7 meter per second. After it expands, the velocity becomes 3.11. Okay, the velocity becomes 3.11. So the velocity after expansion drop, and the pressure initially is so what's the pressure? The pressure initially is 150 kilopascal. So after it expand, it increased to 167 kilopascal. So why is that the case? So when the speed is high, the pressure is low. When the speed is low, the pressure will be high. That's the normal relationship between these mechanical energy. Okay. 8.7 Piping networks and pump selections. So when it comes to industrial processes, there are many piping connected to different processes. Sometimes the pipes are connected in series, and sometimes they are connected in parallel. So for pipes in series, the flow rates is the same in each pipe. So the flow rate at point 1 equals to the flow rate at point 2. The total head loss is the sum of the head losses in individual pipes. So you want to find the head loss from point 1 to point 2, you need to add up the head loss in pipe A and head loss in pipe B. For pipes in parallel, okay, for pipes in parallel, so here is the figure shows the pipe in parallel. So what happens is that the fluid flow from point A. As it reaches the point A, the fluid branches out into branch 1 and branch 2. Okay, so the branch 1 and branch 2, they are parallel to one another. They are different in diameter, different in length, therefore they have a different friction factor. But when it comes to head loss, okay, when it comes to head loss, the head loss at branch 1 will be equals to the head loss at branch 2. So the head loss at branch 1 equals to head loss at branch 2. But flow rate at point A will be equals to the flow rate at point B. So, and then after the point A, the fluid branch into branch 1 and branch 2, and the flow rate flow in the branch 1 must be adding with the flow rate at branch 2, that it equals to the flow rate at branch B, sorry, it equals to the flow rate at point B and equals to the flow rate at point A. Alright. The relative flow rate in parallel pipes, okay, so these are parallel pipes. The relative flow rate in parallel pipes are established from the requirement that the head loss in each pipes be the same. So as we know, in the parallel pipes, the head loss at branch 1 equals to the head loss at branch 2. Okay, so we equal the head loss. Alright, and then we can write down the head loss equation. Okay, the head loss equation, it has a friction factor, the length of the pipe, diameter of the pipe, and the velocity in the average velocity in the pipe, and also the gravity. So we equal both sides, okay, at branch 1 and branch 2. So we equal the branch 1 and branch 2 head loss, and then we can rearrange for the velocity, and then from the velocity we can make it into volumetric flow rate by multiplying the velocity with area. So we have area, cross-sectional area for branch 1, cross-sectional area for branch 2, and then of course we will come up with this equation. So the flow rate in one of the parallel branch, okay, the flow rate in one of the parallel branch is proportional to its diameter to the power 5/2. So this is d to the power 2, this is d to the power half. So we combine these two, that will be 5/2. Alright, so V will be proportional to the diameter to the power 5/2 and is inversely proportional to the square root of its length and friction factor. So this is 1, okay, for 1, and then this is 1, and this is the below here we have 1. So it is proportional to the diameter to the power 5/2, but inversely to the square root of its length and friction factor. And the analysis of piping network, okay, the analysis of piping networks is based on two simple principles. The conservation of mass throughout the system must be satisfied. This is done by requiring the total flow into a junction, okay, a total flow into a junction, flow in into a junction, to be equal to the total flow out of the junction. So the total flow out of the junction is the same as the total flow in into the junction. Okay, total flow means the mass flow rate. Okay, so if the density is a constant, then you have a volumetric flow rate is the same. All right. So and then second, the pressure drop does the head loss. So if you know the pressure drop, you can calculate for the head loss because P equals to rho GH. The pressure drop between 2 points or the head loss between two junction, okay, must be the same for all path between the two junction. This is because the pressure is a point function and it cannot have two value at a specific, okay, as a specified point. So the pressure here and the pressure here must be if the pressure here has certain value, the value is always the same. All right, and the pressure here is also always the same. That's why these two pressure, they are different. Means to say that pressure at point A is greater than pressure at point B due to head loss, and this pressure point, they are always the same for between these parallel pipe. So as a result, their head loss must be the same because head loss is based on pressure loss, okay, pressure drop. Okay, In practice, this rule is used by recording that the algebraic sum of the head losses in the pipe for all loops be equals to 0. So that means that if you from here to here you have a head loss, and then here to here you complete the loop. Okay, so here to here, if you move from point A to B, and then from point B to A, you have a complete loop. So okay, a complete cycle. So point A to point B, you have a head loss. Point B to point A, you got a head gain. Okay, so if you here you have a minus, here you have a plus, so in total you have 0. Okay, that's what it means. So it must be equal in a loop, for all loop must be equal to 0. This slide shows the piping system with pumps and turbine. So we use this as an example. So in this example, we want to pump the water from reservoir 1 to reservoir 2. So reservoir 2 is located higher than reservoir 1. So in order for the water to move from reservoir 1 to reservoir 2, we need a pump. Alright. So this pump will give this energy to push the water from point 1 to point 2. So what we can do, we write the energy equation in the forms of head. So we have this Bernoulli equation, and then with the head coming from the pump, then will be equals to the Bernoulli equation plus the turbine, if there is any turbine in between, and then of course plus the head loss. Head loss for the water to flow in the pipe through the head loss through the pump, head loss through the pipe again, and then head loss into the reservoir number 2. So in this case, we can see that since it's a reservoir, the pressure at point 1 and pressure at point 2 are the same. They are at atmospheric pressure. As a result, we can cancel out the pressure. And then reservoir 1, the water does not move very fast. It's more or less constant or near 0. And same goes to the reservoir 2, where the velocity is near 0 or constant. As a result, we can cancel out the velocity as well. And then if you look into this flow system, that we only have a pipe. Okay, so we only have pipes and pumps. We don't have turbine. As a result, turbine also can be cancelled out. As a result of those cancellation, we left with H pump equals to Z2 minus Z1 plus head loss. Head loss for the entrance, for the head loss in the pipe, for the head loss in the pump, for the head loss in the pipe again, for the head loss for exit. Okay, so these are the head loss we are facing, minor and major. Alright, so we just lump it up, call it head loss. So and then this H pump, we can actually multiply with the mass flow rate and gravity in order to get the power. So here you see they multiply the rho, the volumetric flow rate and gravity on the H pump. So this rho multiplied with volumetric flow rate, that will give us the mass flow rate. So the mass flow rate multiplied with the gravity multiplied with the H pump, that will give us the power. So we know the amount of power that been supplied to the water to move from point 1 to point 2, and if we know the efficiency of the pump, okay, if we know the efficiency of the pump, then we can know the power that is given to the water through the through the shaft, okay, through the shaft. And then if we know the efficiency of the pump and the power, we can also estimate the amount of electricity that goes into the pump. So keep in mind that the electricity is the main source of energy, where the motor get the energy from. So as a result, this electricity, only a portion that is converted into shaft energy due to motor inefficiency. So this case, the efficiency of the motor is about 90%. So let's say 100 watts of energy coming in, only 90 watts actually transfer into the shaft energy. And then from the shaft energy, from the shaft power, a portion is supplied to the water, also is given to the water. Okay, and then this efficiency is only how much? Efficiency by the pump is only 70%. So let's say we have here 100. Just now we say from 100 watt become 90 watt. Now from 90 watt, 90 watt we have to multiply with 0.7. Then we get how much energy, how much power that is actually supplied to the water. So we have two stages of losses: loss due to the motor and loss due to the pump itself. So this is the exactly the situation we are dealing with. So when we know the amount of water actually being taken up by if we know exactly the energy, the power that is being taken up by the water, we can back calculate to determine the power coming from the shaft. If we know the efficiency of the pump, we can even calculate the source of power if we know the efficiency of the pump and motor. Alright. In this example, 8.7 is about pumping water through two parallel pipes. Okay, so we have been talking about what we call parallel pipes. Now we look into the example regarding parallel pipes. Alright, water at 20 degrees Celsius is to be pumped from a reservoir ZA, which is 5 meter above a reference point, to another reservoir at a higher elevation ZB equals to 13 meter through a two 36 meter long pipes connected in parallel as shown in figure 850. So this is figure 850. So this length, okay, length 1 is 36, length 2 also 36. They are parallel to one another. The difference is that this one for pipe 1 has a diameter of 4 cm. For pipe 2 it has a diameter of 8 cm. Alright, so the pipes are made of commercial steel, okay, commercial steel, and the diameter of the two pipes are 4 and 8 cm, okay, respectively. Water is to be pumped by a 70% efficient motor pump combination. So you have a pump, okay, here, which is it has motor and the pump together, and the efficiency is only 70%. That draws 8 kilowatt of electricity power during operation. So from 8 kilowatt, 70% of 8 kilowatt will be supplied to the water, okay, in terms of power. The minor losses and head loss in the pipes that connect the parallel pipes to the two reservoir are considered to be negligible. So the loss of the pipe somewhere here and somewhere here, they are considered negligible. And then we are asked to determine the total flow rate between reservoir and the flow rate through each of the parallel pipe. So you want to find the flow rate from here to here, and also individual flow rate for pipe 1 and pipe 2. Okay, know that we are given the what I call the temperature of the water. Okay, the temperature of the water is 20 degrees Celsius. So we can refer to tables to find the density of water at 20 degrees Celsius for the density of water, and also the dynamic viscosity. And we can refer to the what I call the diagram. We find the diagram for the roughness. For the roughness value. Okay, so the roughness value for commercial steel, okay, for commercial steel is 0.045 millimeter. 0.045 millimeter. 0.045 millimeter. So that means you get 0.00045 meter, because we convert from millimeter to meter. All right, and then we know that the power from 8 kilowatt, only 70% is of the energy is given to the water, is absorbed by the water. So 8 kilowatt and divided 8 kilowatt here, you have okay, you have this electricity 8 kilowatt equals to mass flow rate multiplied with gravity multiplied with H pump over the efficiency of the pump and motor. So we know that the electricity provided is 8000 watt from 8 kilowatt, and then the efficiency of the pump and motor is 0.7 because it's 70%, okay, 0.7. So we take 70 divided by 100, you get 0.7. And then we know the density of water at 20 degrees Celsius is 998 kilogram per meter cube. The flow rate, this is what we want to find. The gravity we know is 9.81, and the H pump we want to find. Alright, so we have one equation. And then the second equation is that we need to write the energy equation for point A and point B. So realizing that is atmospheric pressure, so we cancel out the pressure. It is reservoir surface, the velocity is almost zero, so we cancel out velocity. So you only get with H pump equals to ZB minus ZA plus head loss. Okay, head loss. So we know that ZB is 30 meter, ZA is 5 meter. So therefore we have another equation here. Alright, we have another equation. This is our second equation. And then our third equation, of course, because we know from the theory we discussed before that for parallel pipe, the head loss, what we call the head loss for the parallel pipe, they are same. They have the same head loss. So head loss pipe 1 equals to head loss at pipe 2, which are parallel. Okay. So head loss equals to H loss in pipe 1 equals to head loss at pipe 2. So head loss here equals to the head loss over here. Okay. Then we can also find the volumetric flow rate. So we know the volumetric flow rate is equals to A multiplied by V. So now we can take the V equals to the volumetric flow rate divided by the cross-sectional area. So in this case, the volumetric flow rate is something that we want to find, we don't have, but we are given the diameter of the pipe. Okay, we are given the diameter of the pipe. The diameter of the pipe 1 is 4 centimeter. The diameter of the pipe 2 is 8 centimeter. So we could place in the velocity for pipe 1, the velocity for pipe 2. So we will get these forms of equation for equation 5 and equation 6. And then we can also find the Reynolds number, because Reynolds number is equals to rho Vd over dynamic viscosity. So we know the rho of the water at 20 degrees Celsius. We know the dynamic viscosity at 20 degrees Celsius. And then we want to find the velocity, and then we know the diameter, which is 0.04, which converted from 4 centimeter. We can do the same for pipe 2. We end up more or less the same equation. So the water property remain the same, only the velocity we want to find that is not the same, and also the diameter not the same. Alright, and then we can also use the Colebrook equation. As you know, the Colebrook equation is written in this form, and we want to find the in the Colebrook equation we have this roughness, diameter of the pipe, Reynolds number, and the friction factor. So roughness we already know is roughness for commercial steel, we already refer to the table, is 0.000045 meter. So in this case, we just put in this value, and the diameter we know is 4 centimeter, which is 0.04 meter. And then Reynolds number is for 1 is here, for pipe 1 is here, and the friction factor is what that we want to find. And we write the same Colebrook equation for the second parallel pipe, and then we do the same for the head loss equation. We know L, we know D, we want to find V, we want to find head loss for parallel pipe 1, we want to find the friction factor, we want to find the velocity. Same goes for the parallel pipe 2. So we want to find the head loss in the parallel pipe 2, friction factor for the parallel pipe 2, and the the velocity in the parallel pipe 2. And then we know that the volumetric flow rate, the incoming volumetric flow rate break into volumetric flow rate contributed by parallel pipe 1 plus the volumetric flow rate flow in the parallel pipe 2. Okay, so all these equations, we have all these equations, about 13 equations. So we try to solve it, either do it manually, or we use some software to help us to solve this problem. So in the end, we will come to the solution where we will find this volumetric flow rate is 0.03, and then the volumetric flow rate in the parallel pipe 1 is 0.00415 meter cube per second, and the volumetric flow rate in the second parallel pipe is 0.0259 meter cube per second. So if you take this V1, this volumetric flow rate 1 plus the volumetric flow rate 2, you will get the incoming volumetric flow rate or the outgoing volumetric flow rate. So basically that means this value coming here is equals to the summation of the flow rate here and the flow rate here, and then equals to the flow rate here. Okay, so basically the flow rate here and the flow rate here, they are the same. Okay, and the flow rate 1 and flow rate 2 add together will give the flow rate here as well as the flow rate over here. Alright, I hope that makes sense to you. And then of course we can, when we know that, we can already know the velocity at parallel pipe 1, velocity at parallel pipe 2, head loss at 1, head loss at 2 is the same. H pump, we can also find out the value. We know the Reynolds number 1, Reynolds number 2, friction factor 1, friction factor 2, and here we can see that the Reynolds number is greater than 4,000 value, so we can say that it is in turbulence flow. Alright, so this kind of question is very long. It's good for practice, but this kind of question rarely come out in the exam because the amount of time that required to solve this problem, most probably if you use paper or use manually, it would take up to at least half an hour or perhaps more. So it's a good question for training, but not a question that would come up in a exam or final exam. Alright. Okay, now let us look into example 8.8, the gravity driven water flow in a pipe. Okay, so water at 10 degrees Celsius flows from a large reservoir to a smaller one through a 5 centimeter diameter. So the diameter is 5. Alright, and then this is a large reservoir. The water flows through here and then get into the smaller reservoir. Alright, and then this pipe, okay, is made of cast iron. Okay, cast iron. Alright, determine the elevation. So we want to find the Z1. Okay, for a flow rate of 6 liter per second. So what does it mean? It means the water flowing through here is 6 meter cube per second. Okay, so 6 liter per second. Okay, same as here, 6 liter per second. So our job is to find Z1. So with this information given, we could establish a database based on that. So let's see. Okay, at 10 degrees Celsius, okay, 10 degrees Celsius, we find the density of water. Okay, we try to find density for water. So 10 degrees Celsius, we need to look into table. Alright, so hopefully you can locate this table in the e-learning or the books. Okay, so find the water, property of water. So at 10 degrees Celsius, okay, 10 degrees Celsius, the density of water is 999.7, okay, kilogram per second, And then the dynamic viscosity, of course, it depends on what kind of parameter you want. But most of the time in fluid mechanics, in the case that we're dealing with, we are looking for density of liquid, okay, especially water, density, dynamic viscosity of the water. Alright, so in this case it's 1.307 multiply 10 to the power negative 3 kilogram per meter per second. Okay, so now what we need to do, we just need to write it down. Okay, density of water 999.7 kilogram per meter cube. And then this dynamic viscosity 1.307 multiply 10 to the power negative 3 kilogram per second per meter per second. Okay, and then what else information do we have? We know that the diameter is 5 centimeter, so diameter 5 centimeter, so we convert it into meter, 0.05. so keep in mind we always use meter because it is easier for us to do calculation. So the if you don't use this unit SI, you could get a wrong calculation. So I always convert all the calculation to unit SI. Okay, so always do that. And then this is a cast iron. Okay, cast iron. So for cast iron, we can find the epsilon, the friction factor. So the friction factor for cast iron, okay, cast iron 0.26. 0.26, what's the unit? Millimeter. Similarly, we convert it to meter, 0.0026. Okay, all right, and then what else? We are asked to find Z1 for the flow rate of 6 meter cube per second. So the question is now, what is Z1? And then we know the flow rate, which is 6 liter per second. We know that 1 meter cube per second. 1 meter cube is equals to 1 liter, 1000 liter. All right. So now this one we can get it as 0.006 meter cube per second. So we just need to take 6 divided by 1000, so we'll get meter cube per second. Okay, and since we have epsilon, we can also divide with the diameter. That would give us 0.00026 divided by 0.05, and the answer would be 5.2, 10 to the power negative 3. Okay, what else can we do out of this? So we want to find Z1, right? So if you look into this equation, to find Z1, obviously we need to do this energy equation, okay, the Bernoulli equation plus this pumping, turbine, head loss kind of thing, right? So we do it for Z point 1 and point 2. So we write the energy equation for point 1 and point 2. Alright, so we just write it out. P1 rho g, okay, V1 2g, Z1 H pump, P2 rho g. Yeah, I think I make a mistake in the equation. Okay, there will be alpha 1 here, okay, for the correction of the velocity, of the average velocity correction. So here will be alpha 2, V2, 2G, Z2, H turbine, plus H loss. So this H loss has two components, major plus minor. Alright, so looking into this problem, we realize that velocity we can cancel out because at the reservoir we see the water is not moving. Actually the water at the surface of the reservoir are not moving, or if there is a velocity, the velocity is very low, so near zero. So V1, V2, 0. So in this case we can actually cancel out velocity, okay. And then if you look here, it is open to the atmosphere. So at point 1 and point 2 it is at atmospheric pressure. They are at atmospheric pressure. So since they are the same, it can be also cancelled out, okay, can be cancelled out as well. So if you look here, there's no pump, there's no turbine. So as a result, H pump, H turbine cancel out. So that would leave us with Z1 equals to Z2 plus H loss. Alright, so Z2 we already know, 4 millimeter, okay. So we have Z2, sorry, Z2 not 4 meter, Z2 is 4 meter, okay, Z2 is 4 meter. Alright, that's okay. Okay, that's okay. But this one, HL, head loss, we don't have. Okay, we don't have the head loss. Okay, head loss we don't have. All right, we don't have head loss. Okay, so we need to find head loss. How can we find head loss? So we must look at the energy equation. Okay, and not energy equation, this is a head loss equation that include both minor and major. Alright, so where is this equation? Yep, so this is the equation. Alright, for major loss and minor loss. Okay, major loss and minor loss. So we need to find out, we need to write this equation down. Okay, so head loss, major plus minor, so it's F, so it's F L over D F L over D. L is the length of the pipe, D is the diameter of the pipe, and then summation of KL, loss of coefficient, minor loss, okay. And then to close the bracket, average, okay, average velocity square over 2G. So looking into here, we don't have the value for F, okay, but we can find the value for L, okay. So what's the L? Look here, L, right? So from here, the length of this pipe and the length of this pipe is together, they are 80 meter, okay. And then the length of the vertical pipe is 9 meter. Alright, so we have 80 plus 9, okay, 80 meter plus 90 meter. So we have 80 plus 9. So total is 89, right? Total is 89 meter. So now we have L. D we already know, the D value is known, which is 0.05 meter. Okay, so we have D. Okay, KL, yes, we can find KL. Let's find the loss of coefficient, the KL, summation of loss coefficient. This is minor loss. Okay, so how many minor loss we have? We have here this value. We have here this value. Okay, the loss as a result of entrance. Okay, the loss as a result of 90-degree bending. Okay, this value, 90-degree bending again, so 0.3 again, and then the exit point, so we have this value. So what we do, we just write out, we just gather all this value. Okay, we just gather all this value. So we have 0.5 loss coefficient at the entrance, 0.5, and then we have 0.3 two times, 0.5 once. Okay, 0.5, 0.3, 0.3, and then 1.06. Oh, sorry, I think I missed one more. There is another one called this. Okay, gate valve. Okay, 0.2. So 0.5 plus 0.3 plus 0.3 plus 0.2 plus 1.06. Okay, so 0.5 plus 0.3 plus 0.3 plus 0.2 plus 1.06. So the answer is total 2.36. Alright, 2.36. Okay, so that means we have this, the sum of loss. Alright, the sum of loss coefficient. Now, how about velocity? Do we have the value for velocity? So to get velocity, the velocity that flow in the pipe, okay? The velocity that flow in the pipe. This flow in the pipe. Okay. Let's see. Okay, for the water that flow in the pipe. Okay, we need to find the velocity. Alright, we want to find the velocity in the pipe. So we know the flow rate is this. Okay, the flow rate is 0.006 meter cube per second. Okay, we know the diameter as well. The diameter is 0.05. Alright, so we can form the equation. Okay, volumetric flow rate equals to A cross section velocity. Okay, velocity, the average velocity. Okay, the average velocity in the pipe. So we can write down the equation as volumetric flow rate pi per 4 d square v average. So we have the volumetric flow rate. The volumetric flow rate is 0.006 meter cube per second. And we have pi over 4. Oops. Okay. we have pi over 4. The d value is, the diameter value is 0.05 meter square, then v average. Therefore the v, okay, the velocity value would be, what will be the velocity value? Let's see, the velocity value is 3 point 3.056 meter per second. Okay, now we have the velocity. Alright, and the gravity we know. Okay, no problem. Now what is missing? Obviously is the F value. F value is the friction factor. Okay, friction factor. So to find friction factor, we have to use Colebrook equation. So let us write down the Colebrook equation. So Colebrook equation is written as 1 over a root square of friction factor equals to negative 2.0 log epsilon over diameter divided by 3.7 plus 2.51 over Reynolds number multiplied with the friction factor square root again. Okay, so epsilon divided by diameter, we have it. Okay, we have both of these. Okay, we know this value. Alright, and then Reynolds number we don't have. Of course, the F is what we need to find as well. So we need to find the Reynolds number. Okay, so Reynolds number, hold on. Reynolds number equals to rho v d. V the average velocity, d diameter, rho density over dynamic viscosity, mu. Okay, so we have the rho. Okay, we have the v we just calculated. We also have the d, we also have the mu, which is the dynamic viscosity. So we just place in those values. 999.7 kilogram meter cube, v 3.056 meter over second, and the diameter 0.05 meter over mu 1.307 multiply 10 to the power negative 3 kilogram per second per meter per second, and the value is the value is 116.873. So that's the Reynolds number. Alright, now we have Reynolds number. So we have the Reynolds number. Okay, so we need to find the F value. Okay, so can we find the F value, the friction factor value? We can rearrange the equation again. Okay, we can try to rearrange the equation again. F equals to 1 over
negative 2 log diameter 3.7 plus 2.51. Okay, in bracket, and okay, all right, and then we can place in the value to find the friction factor. -2 log epsilon is this epsilon over diameter is 5.2 multiply 10 to the power -3 over 3.7 plus 2.51 over the Reynolds number that we just calculated, 116873, and the friction factor in the square root. Okay, so you see we have two F here. Okay, we have the F over here, and then we have an F over here. So you know, to find the F, we need to know the F first. So that's the situation we are facing. So what can we do? We can use trial and error method to estimate the F value. So we make an initial guess, for example. Alright, now we guess initial GUESS, guess for friction factor. Let's say we pick 3. Alright, so find out the F. So at initial value F0. So what is the F1? So let's say this is F0, this is let's say this is F0, then now we find F1. Okay, now we try to find F1. Alright, so I have done the Excel sheet so that I can show to you how this is being done. To find F, apart from Colebrook equation, we can also use Moody chart. Alright, we can use either one of those methods. So here I want to show you two methods, but the one method is using Colebrook equation. So now we know the epsilon value. The epsilon value is 0.0. Did I get the epsilon value correct? That's a question. Right, let me see. So what's the epsilon value? The epsilon value is let me see, maybe I did some mistake here. Okay. Oh, so it's 315. Okay, so it's 315. Alright, so we put in the epsilon value, which is 0.26 millimeter, but then if we divide with 1000 we get meter, so it is in meter. And then the diameter, we already know the diameter is 5.2, sorry, the diameter is 0.05 meter, alright, which is 5 centimeter divided by 100, you get 0.05 meter. And then the Reynolds number, we already calculated, which is 116,873. Okay, 116,873. So we should then we the equation here is originally Colebrook equation is like this, and then we arrange it into this form, and then this is how we make the first calculation. Okay, so the formula here is over here. Okay, it's over here. All right, and then initially we guess number 3. Okay, so you see we still get the 0.031519. So this is the first value, so we get the f value, and then this f value we will put into as okay, we guess the value here 3. Okay, then this is f0, then we get f1. Alright, so the f1 we get is 0.030814. so initially we put here 3, then we calculate, we get 0.030814, and then this value will be placed in here, and then we calculate again. So when we calculate again, we get 0.031528. Okay, so we repeat this calculation over and over. This is what we call trial and error method. So we put in the calculate, so we see the value after 3 calculation, the fourth iteration, it becomes stable. So this is the correct value, 0.0315. Okay, so you might ask, but if we use other value, 1000, is that okay? Yeah, still you will come back to the original value. You can put 1 million. See, you will come back to the original value. So the initial value you guess, you will still, it doesn't matter that much, because you can still get back the correct value. Alright, so this is the method number 1, which help us to calculate the friction factor. So now we know for sure the friction factor is 0.031519. 0.031519. So we put in here 3. Okay, 0.030814. 0.030814. Is it correct? Okay, then we calculate for f2 second time. The f2 is okay, 0.031528. Then we calculate for f3 for the third time iteration, 0.031519. And f4 0.031519. Alright, so we know this value becomes stable, so we know for sure the f value. So this will be the f value. Okay, this will be the f value. So we know the f value. So coming back here, we look into this here, this equation, head loss equation. So now we have the f value. Okay, we have the F value. Okay, so we can calculate the HL, the head loss. Okay, which the F is 0.031519. The length 89. Okay, the diameter, what's the diameter? 0.05. The sum of head loss 2.36. The V square 3.056 square over 2G. Alright, so what's the value? What's the value? Okay, let me calculate. 31519. 31519 multiply 89 over 205. And is 7.8. Okay, 27.8. So it's similar. So we get 27.8. Okay, head loss in meter. Okay, and so we actually interested to find the Z1. So obviously now Z1 equals to Z2 plus HL. We know Z2 is, what is Z2? Z2 is 4 meter. Okay, so we have 4 meter plus 27.8 meter, and the value is 31.8 meter. Okay, is it correct with the answer from the book? Yeah, it's more or less the same. Alright, more or less the same. Okay, so let's look into the second example to estimate the friction factor using Moody chart. Okay, using Moody chart. Okay, first of all, you need to prepare the epsilon over diameter value, so which is 0.0052, and then the Reynolds number 1.17 multiply 10 to the power 5. Yeah. Alright. So epsilon value 0.052. 0.052 somewhere here. Okay, somewhere in this line. So so 0.05 is yeah, somewhere between here, 0.052. Alright, somewhere between this line, and then you have to follow the curve moving up. So if you come up here, you might get more or less the same. So and then for the Reynolds number is 1.17 about 1.2 10 to the power 5. Okay, 1.2 10 to the power 5, 1.2 multiplied 10 to the power 5 for the Reynolds number. 1.2 10 to the power 5. So here is 10 to the power 5. This is 1. Okay, here this line is 1 multiplied 10 to the power 5. 1.2. This line is 1.5. Yeah, 1.2 is somewhere here. Yeah, somewhere in this line. So I draw a vertical line, right? And you can see that 0.05 here is almost in the middle between 0.04 and 0.004, between 0.004 and 0.006. So it should be in the middle. Even though it is up here, it should be in the middle as well. Okay, so this blue, you just need to follow curvature up. Okay, follow the curvature moving up. Okay, so it should be a blue line, something like that. Yep, it should be a blue line. Okay, and then meet with this, and we draw a horizontal line. So you see that it crossed 0.03. So you have 0.03. So this is above here is 0.032. Okay, 34, 35, 38, 032, 32, 0.032, 34, 36, 8, and 10. And we'll get 4. So the value should be between 0.03 and 0.032. So you could say that it looks like in the middle, almost in the middle. Yeah, they're almost in the middle. 0.03. Is it correct? Let me see here. Yeah, this line should be slightly higher. Alright, so it's about 0.031. Okay, 0.031. So you could say the value from reading from this chart, the F value that we are going to find, that we are finding is 0.031. Okay, 0.031. So 0.031, if you compare with the value we find from Colebrook equation, so you see Colebrook equation is 0.0315. So we found what we found from Moody chart is 0.031. So it's quite close but not exactly. So if you ask me which is more accurate, of course you should use Colebrook equation, because it will be more, it will give you a more higher accuracy in terms of decimal point. Right, so that's pretty much. Keep in mind, in your exam you will be asked most likely to use Moody chart. If not, you will be asked to use Colebrook equation. So most likely you will be asked to use Moody chart. So make sure you familiar yourself with Moody chart. Okay. This is example 8.9, effects of flushing on flow rate from a shower. So please take a look on that. Try to understand the question diagram, the flow steps, okay, and the calculation, okay, and the final answer. So if we have time, we will talk about it more in details.